Hello there and welcome to Just About Earth, where curiosity slows its breathing a little, where the planet is still wonderfully strange, and where science is allowed to speak in a quieter voice. Tonight we are heading to one of the coldest places on Earth for a mystery that, at first glance, looks almost impolite. In a landscape built from ice, stone, wind, and silence, there is a place where a glacier appears to bleed. Not metaphorically in the usual documentary sense, not in the way people say a sunset bleeds into the clouds, but in a startling, literal-looking streak of red that runs down white ice, as if Antarctica itself has had a small but dramatic accident. It is called Blood Falls, which, to be fair, is exactly the sort of name you would give something if you discovered it in a frozen desert and wanted future generations to remain deeply unsettled. And yet, as strange as it looks, it is real, it is natural, and it has kept scientists busy for well over a century. Blood Falls is a red outflow at the terminus of Taylor Glacier in Antarctica's McMurdo Dry Valleys, and the colour comes from iron-rich, hypersaline brine emerging from the ice and reacting with the air. Before we get into that red stain in the ice, I want to ask you something simple. Where are you listening from tonight? What time is it where you are right now? Maybe it is late enough that the room has gone quiet and the day has finally stopped asking anything of you. Maybe it is early, and this is the gentle start before everything becomes emails, errands, traffic, dishes, and all the rest of it. Either way, I like the thought that while we're talking about one remote corner of Antarctica, people are arriving here from kitchens, sofas, bedrooms, trains, and half-finished evenings all over the world, each of us sitting in our own version of the hour. It feels fitting somehow. A story about a place locked in ice, told across different clocks, different weather, different lives. Somewhere, someone is listening with rain on the windows. Somewhere else, somebody has a fan humming in warm air. And in the far south, at the edge of a glacier, red water waits behind ice that looks as though it should keep every secret forever. If this is the sort of thing you enjoy, something calm, curious, and just a little uncanny, then do consider liking the video and subscribing. It helps this quiet little corner of science reach other people who also like their mysteries explained slowly, preferably without anyone shouting over dramatic music. There is already enough shouting in the world. Antarctica, for all its oddities, does not need it. It already has a glacier with what looks like a wound in it. That is more than enough theatre for one evening. And if you do stay with me for this one, I think you will find that the real explanation is somehow even better than the first impression, because what seems at first like a simple visual shock turns out to be a story about ancient water, buried salt, trapped chemistry, and life making a living in conditions that seem entirely unreasonable. Now, when most of us think of Antarctica, we imagine a place stripped down to a few basic ingredients. Ice, of course. A lot of it. Wind, certainly. Then maybe penguins, though they are rarely standing exactly where the documentaries would have you believe, always conveniently arranged against perfect snow in excellent lighting. We think of a continent so cold and so remote that it feels less like part of Earth, and more like Earth doing an impression of another planet. It is the place we use as shorthand for extremity. If somewhere is unimaginably cold, it is Antarctic. If something survives in harsh conditions, someone will eventually say it is like Antarctica, or Mars, or perhaps both if funding is involved. What we do not usually picture is liquid water slipping from a glacier in a dark red stain. We certainly do not imagine it in a place called the Dry Valleys, which sounds less like a corner of Antarctica and more like a housing development, where the brochures promised scenic views but forgot to mention the existential dread. And yet the McMurdo Dry Valleys are real, and they are among the strangest landscapes on the continent. They are cold, barren, and famously dry, with conditions so severe that snow and ice do not behave there in quite the way we expect elsewhere in Antarctica. These valleys are often described as one of the closest places on Earth to a Martian environment and tucked into this severe setting is Taylor Glacier, where Blood Falls emerges and stains the ice below. What makes Blood Falls so immediately gripping is that the scene seems to deny the rules of its own setting. A glacier is supposed to be solid, sealed, dependable in its frosty way. It may crack, shift, creep forward, grind rock into powder, and ruin the day of anyone who forgot that ice can behave like a very slow machine. But it does not seem like the kind of thing that should leak something red. White ice suggests cleanliness, distance, and silence. Red suggests injury, urgency, and things having gone rather badly. Put the two together, and the mind starts inventing explanations immediately. Perhaps something is living in there. Perhaps it is volcanic. Perhaps the glacier has somehow taken a very strong view on interior decoration. For early observers, the mystery was exactly that compelling, because the appearance was so hard to reconcile with the place itself. The first explanations were not correct, but that is often how these things begin. Nature does something odd. The human brain rushes in with confidence, and then spends the next 100 years being humbled in stages. The red flow was first seen by the geologist Thomas Griffith Taylor during the 1911 Terra Nova expedition, and early ideas included the possibility that red algae might be causing the colour. Later work showed the red appearance comes from iron-rich salt water, with dissolved iron oxidizing when the brine reaches the surface and encounters oxygen. That alone would already be enough to make this place memorable. A glacier in Antarctica leaking ancient iron-rich water that reddens in the air is not exactly everyday scenery. But what gives Blood Falls its staying power in the imagination is that it feels wrong in a way that is very easy to grasp even before you know the science. You do not need a background in glaciology to understand why people stop and stare at pictures of it. White ice, red stain, frozen continent, liquid seep. It bypasses the more academic part of the mind and goes directly to that old, practical part that notices when something in the landscape does not look the way it should. It is the geological equivalent of finding a damp footprint in the middle of a locked room. Nothing about the site says ordinary, and the more you learn, the less ordinary it becomes. What I like most about this story is that it begins with a simple visual shock and then opens outward into a much larger one. Because Blood Falls is not just a weird splash of colour on a glacier, it is evidence. It tells us that beneath all that cold, something has been moving, waiting, building pressure, carrying chemistry through darkness. It tells us that even in a place that looks dead still, there can be hidden systems at work under the surface for very long periods of time, and that is one of Earth's favourite tricks, really. The ground under your feet may look settled, but inside it there may be heat, pressure, slow mineral change, ancient water, microbial communities, gases, faults, and all manner of things minding their business until one day a clue appears where you can see it. In Antarctica, that clue happened to arrive in a colour humans are extremely bad at ignoring. The water itself is not ordinary meltwater. It is extremely salty, rich in iron, and able to remain liquid in conditions where fresher water would freeze solid, which is one reason the whole system can persist in such a cold environment. Scientists studying Blood Falls have described the source as a subglacial brine system, connected to trapped pressurized salty water beneath or within the glacier, and recent work has linked discharge events to changes in glacier surface elevation and subglacial pressure. There is also something deeply satisfying about the fact that Antarctica, of all places, is home to a phenomenon that sounds at first like tabloid nonsense. A bleeding glacier. It has the quality of a headline designed to make a scientist close their laptop very slowly and stare into the middle distance. But then you look into it and discover that reality, once again, has no obligation to be subtle. It can be completely accurate and still sound made up. In fact, some of the most reliable facts on this planet sound as though they were invented by someone trying too hard. There are fish with transparent heads, mushrooms that glow, lakes that explode, rocks that sail across desert flats, and in the McMurdo Dry Valleys there is a glacier that periodically releases red brine from hidden channels below the ice. Earth does not need exaggeration. It merely needs patient description. Still, this particular place feels different from most natural oddities because it carries a small emotional jolt with it. A red seep in a white world does something to the imagination. Even when you know the explanation, some part of the brain still reacts before the calmer part catches up. It is the same reason rust stains sometimes look more dramatic than they are, why old ships can seem haunted by nothing more than oxidation and weather. Colour carries a lot of baggage, and red, especially, is not a colour we encounter neutrally. It signals ripeness, danger, warmth, alarm, appetite, injury, attention. It belongs to berries, sunsets, warning lights, and human blood. When you see it in a glacier, the mind does not file it away under ordinary chemistry. It pauses, it asks questions, it takes the bait. That pause is where good science often begins. Not with certainty, but with the refusal to walk past something strange. Someone sees an anomaly and does not let it go. Why there? Why that colour? Why liquid here? Why now and not always? How deep does it come from? How old is it? What is dissolved in it? What kind of pressure pushes it upward? Could anything live in it? Those questions are not just the mechanics of research. They are the continuation of the same curiosity that makes any of us lean toward a mystery in the first place. The difference is that scientists then go out into a brutally cold landscape with instruments, field gear, sample bottles, logistics plans, and a tolerance for discomfort that the rest of us prefer to outsource, and that is worth pausing on for a moment. The setting of this story is not just remote in a romantic map atlas sense. It is operationally remote. Studying blood falls means dealing with Antarctica, which is a place that can make simple tasks complicated very quickly. Things freeze, winds shift, access is limited, seasons are short, instruments fail, and every answer costs effort. It is one thing to wonder about a red stain on a glacier from the comfort of a chair. It is another thing entirely to stand in the dry valleys surrounded by rock, ice and cold so uncompromising that even your enthusiasm has to wear layers. That, perhaps, is part of why the story feels so solid and earned. The explanation did not arrive in one neat moment. It emerged through years of observation, fieldwork, better tools, and people willing to keep asking a glacier what exactly it thought it was doing. The newest studies have not changed the basic picture of blood falls so much as sharpened it. The broad explanation remains that iron-rich salty water is making its way out from the glacier and turning red as it reacts with oxygen. But newer work has added detail about how the discharge is tied to changes within the glacier itself, including shifts in pressure and surface lowering during outflow events. In other words, the glacier is not simply staining itself at random. There is plumbing in the dark, and sometimes that hidden system pushes outward hard enough for us to notice. So this evening, that is where we begin. Not yet with the full chemistry, not yet with the buried brine reservoir, not yet with the microbes that turn this place from a visual mystery into an astrobiological one. Though we will get to all of that in time. For now it is enough to stand at the edge of the image and let it settle properly in the mind. A glacier in Antarctica, a place famous for whiteness, a place people associate with silence, cold, and immense stillness. And from it, now and then, a dark red flow appears, as if the ice has opened a narrow seam and allowed something old to speak. Not blood, of course. Something more interesting than blood, because blood would merely mean injury. This means history, chemistry, pressure, survival, and time. This means there is a hidden system beneath the obvious one. It means the landscape has an inside. That, more than the colour, may be the real reason bloodfall stays with people. It suggests depth where we expect closure. We see a glacier and imagine a frozen block. Bloodfalls reminds us that a glacier can also be a container, a barrier, a roof, a pressurized lid over ancient salty water that has not forgotten how to move. It turns the surface into a clue, and once you know there is a clue, the whole setting changes. The white ice no longer looks simple, the valley no longer looks empty. The silence starts to feel occupied. Beneath Taylor Glacier there is a story that did not begin with the red stain people photograph. The stain is just the part that reaches us. The real story has been waiting under ice, in darkness and salt, for far longer than any of us have been around to ask about it. And before we can follow that hidden water downward, before we get to the iron and the brine and the question of how anything remains liquid in such a place, it helps to spend a little time with the landscape that keeps this secret at all, because Bloodfalls does not exist in isolation. It belongs to a valley so cold and dry that even Antarctica starts to look unfamiliar there, and once you step into that setting, the whole thing begins to make a different kind of sense. To understand why Bloodfalls feel so unsettling when you first see it, it helps to spend some time with the place around it, because the setting does a great deal of the work. If that same red outflow appeared on an ordinary hillside next to green grass and muddy ground, it would still be strange, but it would not have quite the same effect. In Taylor Valley, though, it looks like a breach in the rules. The valley is part of the McMurdo Dry Valleys in southern Victoria Land, a region often described as the largest ice-free area in Antarctica and one of the most extreme cold deserts on Earth. These valleys are known for low temperatures, very limited precipitation, salt accumulation, and ecosystems where life exists close to its environmental limits, with microorganisms doing most of the heavy lifting. That phrase, dry valleys, can sound almost contradictory the first time you hear it. Antarctica, after all, is famous for ice. It is the continent most people imagine as permanently buried beneath snow, and in the broadest sense that is true. But the McMurdo Dry Valleys are different. Here, large stretches of ground remain exposed, with rock, gravel and old soils lying open under a sky that can look almost too clear, as if the weather has decided to stop decorating and just show you the bones of the landscape instead. Snowfall is scarce. Moisture is scarce, and the little snow that does fall is often removed or redistributed by strong katabatic winds, those gravity-driven winds that pour down from the polar plateau like cold air with a grudge. The result is a place that feels less like the familiar image of Antarctica, and more like a severe polar desert that happens to be surrounded by ice. Taylor Valley sits within this broader region, and has a geography that seems designed to simplify everything down to essentials. There are glaciers, rock outcrops, bare slopes, frozen lakes, short-lived meltwater streams in summer, and a lot of open ground that looks as though it has not changed in any hurry for a very long time. NASA has described Taylor Valley as one of the most remote and geologically exotic places on the planet, and that is one of those official phrases that sounds slightly dramatic until you look at the pictures and realise they may actually be understating it. The valley is home to Taylor Glacier, Bloodfalls, and a set of features that do not sit neatly in the usual Antarctic postcard. There is very little softness here. No forests, no deep soils, no ordinary riverbanks, no sense that life has been given particularly comfortable terms, and yet that harshness is exactly what makes the place so scientifically valuable. In many environments, weather, water, plants and animals keep turning the landscape over, reshaping surfaces, mixing materials, softening edges. In the dry valleys, many of those processes are limited or absent. The cold slows things down. The dryness limits erosion by ordinary flowing water. The sparse biology means there is far less of the usual living clutter that covers other parts of the planet. So when scientists look at these valleys, they're often seeing a place where geological and climatic signals are unusually well preserved. It is not untouched exactly, because no real landscape is ever frozen in a perfect pause. Wind still moves sediment, glaciers still creep, and summer melt can briefly awaken streams. But compared with much of the world, the dry valleys often feel like a place where Earth has left its notes on the table instead of stuffing them into a drawer. That matters for bloodfalls because the outflow is not just sitting in some random location. It appears at the terminus or snout of Taylor Glacier in Taylor Valley, near the west lobe of Lake Bonny. The glacier itself is part of a cold-based glacial system, meaning the ice is generally frozen to its bed in many areas, rather than sliding rapidly on a cushion of meltwater the way some warmer glaciers do. In the Bloodfalls area, however, hidden brine systems complicate that simple picture. The red outflow emerges from a crack or crevasse in the glacier, staining the ice below and sometimes reaching toward the nearby lake basin. That location is important because it places the seep right at the edge between the glacier's internal world and the exposed surface environment of the valley. Lake Bonny itself deserves a moment, because it adds to the slightly improbable quality of the whole scene. In a place as dry and cold as Taylor Valley, there are lakes, but they are not open blue bodies of water in the usual sense. The lakes in the McMurdo Dry Valleys are typically covered by thick perennial ice, and the biological communities associated with them are dominated mostly by microorganisms. That means the valley is not empty so much as stripped down. The familiar signs of life are few, but life is still there, mostly small, persistent, and very good at enduring conditions that would make the rest of us reconsider our travel plans immediately. Bloodfalls enters this setting not as a dramatic standalone object, but as one component in a valley where water, salt, ice, rock, and microbial life have been negotiating with one another for a very long time. When people hear silence described in a natural landscape, it can sometimes sound a bit exaggerated, because most places are never truly silent. There is usually wind, water, leaves, insects, traffic in the distance, something. Taylor Valley is not silent in the absolute sense either. Wind can move hard through it. Boots crunch. Equipment rattles. Helicopters, when science teams arrive, certainly do not glide in unnoticed like polite owls. But the valley has a stripped-down acoustic quality because there is so little biological noise and so little softness to absorb or disguise the sounds that do exist. When the wind settles, the emptiness becomes more noticeable than the sound. It is a place where your own presence can feel louder than expected, as though the landscape has not entirely agreed to host you and is waiting to see how long you will last. That feeling is part of what gives Bloodfalls its stage. The red outflow does not emerge in a lush or complicated environment full of distractions. It appears against pale glacier ice, dark rock, and the muted tones of a cold desert. There is almost nothing in the scene to compete with it. No trees, no fields, no wet green growth to soften the contrast. Just a stark geological setting that behaves like a blank wall in a gallery, making sure your attention goes exactly where the oddity is. This is one reason photographs of Bloodfalls are so effective. The place is already spare, the colours are already limited, so when red appears, even in a relatively narrow stain, it takes over the whole image. The history of the valley adds another layer. The dry valleys became known to explorers in the early 20th century, and the naming of their many features in the region reflects that era of Antarctic exploration. Taylor Valley and Taylor Glacier are named after Thomas Griffith Taylor, the geologist who was part of Robert Falcon Scott's Terra Nova expedition. The lakes of the dry valleys had already drawn attention during earlier expeditions, and by the time Bloodfalls entered the scientific imagination, this was already a region associated with difficult travel, severe conditions, and a growing awareness that Antarctica was not one simple white mass but a continent of regional oddities. It is worth remembering how strange this valley would have felt to the early explorers who entered it, without the benefit of satellite imagery, decades of glaciology, or the comforting knowledge that a strange stain on a glacier might eventually be explained by chemistry rather than supernatural behaviour. These were people stepping into a landscape that often would have looked less like a normal earthly valley and more like a place some deity had half finished and then abandoned for being too austere. Bare ground in Antarctica is surprising enough. Dryness is surprising. Frozen lakes hidden beneath ice lids are surprising. Then add a glacier that leaks red, and the whole place begins to look as though the continent is experimenting with tone. Still, Taylor Valley is not strange merely for the sake of being strange. It is a very useful natural laboratory. The McMurdo Dry Valleys have long been studied as a Mars analogue because their cold, arid, exposed conditions preserve processes and habitats that can help scientists think about life and geology in extreme environments. Researchers have used the valleys to investigate climate records, permafrost, glacial behaviour, soil ecology, lake chemistry, stream flow, and microbial survival near environmental limits. Blood Falls fits into that broader scientific picture because it is both a local curiosity and a window into systems that are hidden beneath ice. When scientists study the valley, they are not only describing an Antarctic oddity, they're also asking what kinds of physical and biological processes can persist where conditions seem to forbid them. And that brings us back to the mood of the place, because the silent severity of Taylor Valley is not just background scenery, it actively shapes the mystery. A glacier in a wet, temperate environment can leak, drip, melt and run in all sorts of visible ways. People are accustomed to seeing moving water in those settings, but in Taylor Valley the expectation is different. Cold should dominate, dryness should dominate, ice should hold. The whole region encourages the assumption that things are locked down, preserved, and restrained. So when Blood Falls appears, the surprise is not only the colour, but the fact of discharge itself. Something is moving out of a glacier here, in a valley where movement often feels reduced to the bare minimum, and where even summertime activity can seem tentative. Summer, by Antarctic standards, does loosen the valley slightly. Seasonal melt from glacier surfaces and margins can feed ephemeral streams, and the valleys are not static year-round museum pieces. There is hydrology here, but it is pulse-driven and limited, tied closely to temperature and solar conditions. Fresh water in the McMurdo Dry Valleys originates almost entirely from surface and near-surface melt from cold-based glaciers, and these seasonal inputs control the brief flow of streams and influence the lakes below. Even so, that is not the same thing as Blood Falls. Ordinary meltwater belongs to the valley's seasonal rhythm. Blood Falls belongs to a hidden salty source that does not fit the usual summer thaw story. This is an important distinction, because one of the easiest mistakes to make when imagining Blood Falls is to picture it as some kind of red version of everyday glacier melt. It is not that. The outflow is unusual precisely because it comes from a subglacial brine system, not from a bit of surface snow turning liquid on a relatively sunny day. The cold desert environment helps underline that difference. In a wetter or more dynamic landscape, strange seepage might get lost among other forms of water movement. Here, it stands out because the valley is so disciplined. Water, when present, already feels consequential. Unusual water feels even more so. The physical look of Taylor Glacier contributes as well. Glaciers in popular imagination often appear smooth and luminous from a distance, all graceful curves and blue crevasses. Up close, many of them are rougher, dirtier and more industrial looking than people expect, carrying sediment, fractured surfaces and stress marks like an enormous slow machine under tension. Taylor Glacier, viewed in the context of the dry valleys, looks less like an elegant frozen ribbon, and more like a massive body of ancient ice pressing into a basin of rock and sediment. That matters, because Blood Falls appears not on some ornamental alpine surface, but at the working edge of a glacier that has been interacting with the valley floor, buried salts and hidden fluids over long timescales. The valley makes the glacier look substantial, not decorative, which is just as well, because decorative objects are not usually connected to million-year-old brines. Then there is the weather, or perhaps the temperament of the weather, which in Antarctica is often close to the real governing authority. Average annual temperatures in Taylor Valley are deeply cold, commonly ranging roughly from about -15 to -30 degrees Celsius depending on location and season, while annual precipitation is extremely low, on the order of around 11 millimetres water equivalent in some parts of the valley. Those numbers help explain why the place feels so improbable to anyone used to wetter cold climates. This is not a snowy, slushy, half-thawed winter landscape. It is a cold desert where moisture is precious, freezing dominates, and any liquid water system immediately becomes interesting. If you stood there long enough and were somehow comfortable enough to do any reflective standing at all, which is already giving yourself more optimism than most field scientists would recommend, you might begin to notice how much of the valley's personality comes from subtraction. It is a place made memorable by what it lacks. It lacks higher plants over most of the landscape. It lacks familiar animals. It lacks abundant precipitation. It lacks easy access. It lacks the background noise and visual clutter that make most environments feel inhabited. And because it lacks so much, every presence becomes more pronounced. A stream matters more. A patch of microbial mat matters more. A lake under ice matters more. A red outflow on a glacier matters more still. That is one reason the valley feels so quiet in the imagination, even when you're only hearing about it. It invites concentration. There is not much else to look at in a casual way, which means the mind naturally starts examining textures, colours, slopes, cracks, and distances more closely. Bloodfalls benefits from that attention. It is not just a dramatic sight. It is the kind of sight that seems to deserve inspection, and Taylor Valley is exactly the kind of setting that trains the eye to inspect. In a busier landscape, you might glance and move on. Here the landscape almost insists that you keep looking. Scientists have done exactly that, of course, and the site is important enough that the lower Taylor Glacier and Bloodfalls area has formal environmental protection within the Antarctic Treaty System because of its scientific value. The outflow and surrounding glacier zone are recognised as significant for glaciology, paleoclimate work, geomicrobiology, and the study of subglacial processes. In other words, the valley is not merely photogenic in a strange way, it is a protected place, because what happens there helps answer real questions about Earth systems and extreme life. That scientific protection also hints at something else the valley teaches very quickly. Fragile does not always look delicate. Taylor Valley can appear tough, stripped, almost indestructible. It is all rock, ice, and cold. It looks like the sort of place that would shrug at any insult. But environments like this can be remarkably sensitive to disturbance, precisely because change is slow and biological communities are limited. Tracks can last, contamination matters, small inputs can have long consequences. The silence of the valley is not just atmospheric, it is part of an environment where processes are sparse enough that interruption carries weight. So the place where Bloodfalls appears is not simply empty Antarctica. It is a very specific valley with a very specific personality. It is remote, cold, dry, windswept, geologically exposed, biologically minimal at first glance, and full of hidden constraints. It is a landscape that makes simple assumptions look foolish. Water may exist here, but not where you expect. Life may exist here, but not in familiar forms. Ice may dominate here, but it does not seal everything shut. The valley looks like the end of a story, but scientifically it behaves more like the beginning of one. And perhaps that is why Bloodfalls feels so memorable even before its chemistry is explained. The valley has already done the groundwork. By the time the red stain appears, you have been taught to expect severity, dryness, and frozen stillness. Then the glacier quietly contradicts all three. It releases liquid, it releases colour, it releases evidence that beneath this apparently disciplined landscape there is something hidden, mobile, and persistent. The valley gives the mystery its silence, its contrast, and its credibility. Once you have taken in the setting properly, the next question almost asks itself, not where is this happening, because now we know that. Not even how can a place this dry and cold allow anything liquid to emerge, though that is close. The more immediate question is simpler and more direct. Why is it red at all? And how can something that looks so much like blood be nothing of the kind? The name Blood Falls does a great deal of work before the science has any chance to speak. The first time people hear it, they tend to imagine something biological, something dramatic, something with a pulse and a wound and perhaps a very distressed glacier. That is understandable. The outflow is red, the setting is stark, and the contrast is so sharp that the eye does exactly what eyes have always done when faced with unfamiliar things. It reaches for the nearest familiar category. Red fluid on a pale surface looks like blood, so the mind calls it blood before the slower part of the brain has time to object. But Blood Falls is not blood in any biological sense. It is not made of cells, it has no hemoglobin, and it has no connection to injury or animal tissue. What emerges from Taylor Glacier is an iron-rich hypersaline brine. The red colour develops because dissolved iron in that brine reacts when the fluid reaches the surface and encounters oxygen, creating iron-bearing material that stains the ice a deep rusty red. Scientists studying samples from Blood Falls have concluded that the colour comes from oxidation of dissolved ferrous iron, or Fe2+, in the subglacial fluid after exposure to air. That distinction matters because real blood is a very particular kind of fluid. In animals like us, blood is a transport system. It carries oxygen, nutrients, waste products, immune cells, and clotting components through the body. It contains plasma, red blood cells, white blood cells, and platelets, and its familiar red colour comes primarily from hemoglobin inside the red blood cells. In other words, blood is not simply red liquid. It is a highly organised biological substance full of cellular parts and proteins doing specific jobs. The red outflow at Blood Falls has none of that internal biology. It is not circulating through vessels. It is not transporting oxygen through a living body. It is not clotting, healing, or responding to injury. It is salty water carrying dissolved iron and other chemical ingredients from beneath a glacier. The fact that both human blood and Blood Falls owe their appearance, in a broad sense, to iron, only makes the visual confusion more effective. The resemblance is real enough to fool the eye, but the chemistry and the context are completely different. That is one of the reasons Blood Falls is such a successful natural illusion. It is not random red dye in ice. It is a colour that lands very close to a colour humans are already primed to notice. We are not neutral about red. We see it quickly, and we interpret it emotionally long before we interpret it scientifically. On a glacier, that response becomes even stronger, because glaciers are supposed to be white, blue, grey, maybe dirty at the edges, but not this. Red is out of place there. It looks like evidence of an event rather than evidence of a chemical process. That is why early observers were puzzled, and why the first explanations were not yet the right ones. When Blood Falls was first observed by the Terra Nova expedition in 1911, one of the early ideas was that the colouring might be due to red algae. That was not an absurd guess at the time. Red and reddish microorganisms can colour snow, water and wet surfaces in other environments, and without the detailed chemistry available later, a biological pigment was an understandable first suspect. But later work overturned that explanation. The red appearance was shown to be tied to iron-rich salt water rather than algae, and more recent analyses have refined that picture further by showing that the surface materials are more complicated than a simple layer of ordinary rust crystals. That newer refinement is important, because for a while the simplest version of the story went like this. Blood Falls is red because the iron in the water rusts when it hits the air. That explanation is broadly correct and still useful, especially if you are introducing the phenomenon to someone for the first time. But scientists are professionally dissatisfied with broad correctness when there is a chance to be more precise. It turns out the colour is not just a neat coating of classic iron oxide in the way many people imagine rust on a garden gate. Detailed analysis of samples from Blood Falls suggests that the red comes from oxidation of dissolved Fe2+ in the subglacial fluid, forming tiny nanospheres of a hydroxylated, mixed-valent iron-containing material. In plainer language, the chemistry is a little messier, finer, and more interesting than the water is full of rust. It is closer to the iron, transforming into very small reactive particles and amorphous materials as the brine leaves its oxygen-poor environment and enters the open air. That phrase, oxygen-poor environment, is doing a lot of work here. Beneath the glacier, the brine exists in conditions very different from the surface world. Down there, the fluid is suboxic or oxygen-free enough that iron can remain in a dissolved reduced form, mainly Fe2+, rather than immediately precipitating into the reddish materials we associate with oxidation. While that brine remains trapped and isolated beneath the ice, it does not look like the dramatic red flow people see in photographs. In fact, one striking detail from later reporting and analysis is that the water emerges clear and then quickly turns crimson after exposure. That is a lovely little scientific correction to the imagination. People assume the glacier is hiding red water. In effect, it is hiding water that becomes red when brought into the Antarctic air. The performance happens at the surface. There is something satisfying about that, because it means the most famous visual feature of bloodfalls is not fully formed in secret below the ice. It is produced at the boundary between two environments. Down below, the fluid stays chemically poised in one state. Up above, the atmosphere changes the script. The iron reacts, oxidizes, and begins forming the materials that give the outflow its reddish colour. It is a good reminder that many natural spectacles are not substances but transitions. A rainbow is not sitting in the sky waiting to be collected. It appears under certain conditions of light, angle, and water droplets. Bloodfalls is similar in spirit. The red is not a stored pigment in the way berry juice is red. It is the visible result of a chemical change occurring as the fluid moves from one set of conditions into another. The word oxidation can sound more intimidating than it is. In this case, it simply means that iron is reacting in a way that changes its chemical state when oxygen becomes available. The everyday comparison is rust. If a steel tool sits out in the weather long enough, it develops reddish-brown corrosion because iron in the metal is reacting with oxygen and moisture. Bloodfalls is not rusting in exactly the same neat household way, but the analogy is good enough to keep us oriented. The brine carries iron in one state beneath the glacier, then when it emerges, that iron shifts into forms that produce the rusty red stain. So the glacier is not bleeding. It is, in a sense, leaking an iron-rich fluid that rusts on contact with the surface world. That explanation also helps with another part of the illusion, which is the question of texture and behaviour. Blood, real blood, is thicker than water and full of cells and proteins. It clots, it coagulates, it has a biological structure and viscosity that matter. Bloodfalls does not behave that way because it is brine. Brine is just very salty water, in this case extraordinarily salty water, carrying dissolved substances from beneath the glacier. Its redness is not the redness of a living fluid. It is the redness of mineral chemistry acting quickly in a place where colour stands out with unusual force. So although photographs of bloodfalls sometimes look gory from a distance, what you're really seeing is closer to an iron-rich seep, staining ice than to any biological analogue. It only borrows the emotional effect of blood, not the substance of it. One reason people remain fascinated by this is that the resemblance is not entirely accidental in the deepest visual sense. Human blood is red because of iron in hemoglobin. Bloodfalls is red because of iron chemistry in brine. That does not make the two things remotely similar as fluids, but it does mean the eye is picking up on a shared element. Iron is central to both stories, just deployed in completely different systems. In one case, it sits inside a protein in red blood cells and helps a body move oxygen around. In the other, it sits dissolved in ancient salty water beneath a glacier and reddens only after a change in chemical conditions. It is almost as if Earth has found two very different ways to use the same element to get our attention. Recent work has made that story even richer by showing that the red material at blood falls includes tiny iron-rich nanospheres, rather than just the expected larger crystalline mineral forms. Researchers using multiple analytical techniques concluded that the colour is influenced by these small, metastable iron-bearing particles, and that other ions also help shape the final appearance. That sounds niche, and it is niche, but it matters because it explains why earlier, simpler descriptions were not capturing the full picture. Scientists were not wrong to connect the redness to iron oxidation. They were just still a few layers away from understanding what the iron was becoming on the surface. The glacier, rather rudely, turned out to be doing finer chemistry than the early summaries allowed. There is a nice lesson in that for anyone who likes science as a process, rather than just a stack of facts. Explanations often improve by becoming less tidy before they become more accurate. At first you have mystery, then you have a rough answer, then the rough answer gets unpacked into a more exact one that sounds a little less elegant at dinner parties but far more satisfying in the lab. Its blood becomes, it's probably algae, then it's iron oxides, then it's dissolved Fe2 plus oxidizing on exposure to air and forming mixed valent iron-bearing nanospheres with colour also influenced by other ions. Somewhere along that road, the public understandably keeps the short version, but the long version is the one that tells you the glacier is participating in a specific chain of chemical events, rather than simply oozing red mineral water like an especially theatrical pipe. It is also worth noting that the red does not mean the brine itself is born bright crimson beneath the glacier. That is one of the more counterintuitive parts. The fluid can emerge clear before turning red. Once you know that, Blood Falls changes from being a spooky reservoir of hidden redness into something more dynamic. The colour is not merely transported, it is produced in motion. It belongs to the meeting point between underground chemistry and surface oxygen. That makes the outflow feel more active, more immediate. The glacier is not opening to reveal a scarlet secret tucked away in a bottle. It is releasing a fluid that transforms in front of the world, and that transformation is what we see. All of this also explains why the word blood remains useful even though it is inaccurate. It is not a scientific word in this context, but it is a powerful descriptive one. The resemblance is strong enough that the name stuck, and from a human point of view you can hardly blame anyone. If early explorers had named it Iron Oxidation Seep No. 1, it would have been more chemically responsible but considerably less memorable, and future generations would have been robbed of one of Antarctica's most effective pieces of branding. The name survives because names do not have to be precise to be effective. Science then arrives afterward to tidy up the misunderstanding. And once science has tidied things up, the place becomes more interesting, not less. That is often the best outcome. A disappointing explanation would have made Blood Falls smaller. Instead, the real answer makes it larger. It is not blood, which would only tell us that something had died or been injured. It is an iron-rich brine system hidden beneath a glacier, in a cold desert, in one of the harshest environments on the planet, with dissolved chemistry preserved in the dark until contact with air flips the colour into view. That is better. It is slower, older, and far less ordinary. The redness is not gore. It is a clue. It is also a reminder that surfaces lie very effectively. What looks like a red waterfall is really a sign of chemical history below the ice. What looks like a wound is actually a reaction. What looks like a biological fluid is a geological and geochemical one. Blood Falls is only misleading if you stop at the first glance. Once you look a little longer, the scene starts to reorganize itself. The glacier is not injured. The glacier is connected. The colour is not evidence of life in the familiar bloody sense, but it is evidence of a system that has remained active and chemically distinct under conditions most people would assume were locked solid. So when people ask why the water is red but not blood, the simplest answer is this: because iron-rich brine from beneath Taylor Glacier reaches the surface, and its dissolved iron oxidizes when exposed to air, creating the rusty red materials that stain the ice. The more complete answer is that modern analyses show the colour involves not just ordinary rust in a casual sense, but tiny amorphous iron-bearing nanospheres and related surface materials formed from Fe2 plus rich subglacial fluid as it transitions into the oxidizing surface environment. And the most useful answer, perhaps, is that blood falls looks biological only because humans are good at pattern recognition and very bad at ignoring red. Once that part is clear, another question steps forward almost immediately. If the fluid is not blood at all but ancient, hypersaline brine full of dissolved iron, then the real mystery is no longer the colour. The real mystery is the source. Where does that brine come from? How did it get trapped beneath so much ice? And how has it remained liquid in a place that seems determined to freeze everything it touches? Once the red colour is explained, the mystery becomes less theatrical and more interesting. The question is no longer why a glacier looks as though it has hurt itself. The question is what sort of liquid can remain hidden beneath so much ice in such a cold place, how long it has been there, and what kind of route it takes before it finally appears at the surface. Blood Falls is only the visible end of that story. The larger part of it is below the ice, out of sight, where Taylor Glacier sits over a system of hypersaline brine and brine-saturated sediments that are not supposed to be there if your mental model of a cold glacier is simple, dry, and neatly frozen all the way down. Taylor Glacier has long been considered predominantly cold-based, with basal temperatures well below the pressure melting point of fresh ice, yet multiple studies have shown that it still hosts an active subglacial and englacial brine system that feeds Blood Falls. That phrase hypersaline brine is worth lingering over, because it is the key to how this whole buried system manages to exist at all. Fresh water freezes at 0 degrees Celsius under ordinary conditions, and in the lower reaches of Taylor Glacier the ice and surrounding environment are much colder than that. But salt changes the rules. When enough dissolved salts are present, the freezing point drops, sometimes dramatically. The brine beneath Taylor Glacier is salty enough to remain liquid at temperatures where ordinary water would be solid, and that basic fact gives the buried fluid its first advantage. The glacier is cold, yes, but the fluid is not ordinary water. It is more like a concentrated chemical survivor, the sort of liquid that can keep existing precisely because it has become inhospitably salty. Researchers have described Blood Falls effluent as saline enough to remain liquid down to about -6 degrees Celsius at atmospheric pressure, and the broader subglacial system is interpreted as being kept liquid by elevated salt content, along with additional heat effects linked to freezing processes. Even then, what lies beneath Taylor Glacier is not best imagined as a single, neat underground lake with a tidy shoreline and one dramatic outlet. That picture is too simple. The evidence gathered over the last couple of decades points instead to a more extensive and connected system of brine-saturated sediments below the glacier, with pathways that can route fluid toward Blood Falls and also toward Lake Bonny. Airborne electromagnetic surveys detected low resistivity zones consistent with conductive brine beneath the lower glacier and in parts of Taylor Valley more broadly, and one study estimated about 1.5 cubic kilometres of subglacial brine-saturated sediments below Taylor Glacier alone. In other words, Blood Falls is not being fed by a little hidden puddle trapped right at the terminus. It appears to be the surface expression of a much larger buried groundwater system. That was one of the most important scientific turns in the whole Blood Falls story. Earlier work had already shown that the red outflow involved iron-rich salty water, but the larger geometry of the source system remained uncertain. Then geophysical surveys changed the scale of the picture. The 2015 Nature Communication study used airborne electromagnetic data to map conductive subsurface zones in Taylor Valley, and found evidence for extensive brines beneath the glacier, beneath lakes and through permafrost-rich valley materials. In the Bonny Basin, the data suggested hydrological connectivity between brine-rich sediments below Taylor Glacier and Lake Bonny, while later glaciological work showed an active and glacial brine pathway within the glacier itself leading toward bloodfalls. So the glacier is not just sitting on top of old salty material, it appears to be actively involved in routing that material through a hidden hydraulic system. That leads to the next question, which is really the oldest one in the whole affair. Where did the salt water come from in the first place? The strongest evidence points to a marine origin, but not in the sense of modern seawater somehow sneaking casually under the glacier while no one was looking. Taylor Valley has a long and complicated geological history, and one leading model is that seawater or marine-derived salts entered the valley system in the distant past, when the valley had a very different relationship to the sea. The Nature Communications paper notes geological evidence that the McMurdo Dry Valleys were a fjord ecosystem during the Miocene, when seawater intruded far inland beyond the current extent of Taylor Glacier. Later cooling and freezing would have concentrated those saline waters into dense brines. The 2019 geochemistry study likewise concluded that the Taylor Glacier subglacial brine is of marine origin, but has been extensively altered over time by rock-water interaction and later processes. Marine origin does not mean the brine is simply ancient seawater, preserved like a perfect bottle in a cellar. It has not sat untouched. It has evolved. That is what makes the chemistry so useful and so messy at the same time. Several lines of evidence support the marine connection. Marine-like major ion ratios, marine chlorine isotope signatures, and microbial lineages related to marine organisms have all been reported from the bloodfall system. At the same time, the brine also bears clear signs of long interaction with bedrock and sediments. High silica and radiogenic strontium signatures indicate chemical weathering and modification rather than pristine ocean water. In plain terms, the ancestral source appears marine, but the fluid we see today is the result of a very long life underground, where salts concentrated, minerals dissolved, and chemistry drifted far from any simple picture of trapped seawater. There is also a second layer to the origin story, and this is where the scientific version becomes more honest than the popular one. You will often see bloodfalls described as being fed by seawater, trapped beneath the glacier for more than 1 million years. That claim is grounded in serious work and remains a useful shorthand. NSF and UAF reporting on the 2017 glaciology study described new evidence linking bloodfalls to a large source of salty water that may have been trapped under a Taylor Glacier for more than 1 million years. But the detailed geochemical literature is a little more nuanced. The 2019 study considers several possible evolutionary pathways, including cryoconcentration of past proglacial lake waters, dissolution of evaporate deposits, and modification and cryoconcentration of ancient seawater, and concludes that the current subglacial brine is marine in origin but has been heavily altered. Meanwhile, noble gas evidence in Lake Bonny has been interpreted as consistent with some subglacial inputs, having residence times on the order of hundreds of thousands of years, up to roughly 250,000 years for certain signals. So the safest way to picture the system is as ancient marine-derived brine, modified and recycled over very long timescales, with the broader source history likely stretching from hundreds of thousands to more than 1 million years, depending on which part of the story you're asking about. That may sound less satisfyingly crisp than "it is a 1,000,000-year-old underground lake," but it is more faithful to the evidence, and in some ways more impressive. A perfectly untouched body of trapped water would be scientifically useful, but conceptually straightforward. What sits beneath Taylor Glacier seems to be something more dynamic. Ancient in origin, yes, but also chemically active, regionally connected and modified by the repeated history of freezing, concentration, contact with sediments, and the glacier's own advances and retreats. The glacier has overrun this system, sealed it, pressurized parts of it, and in some places injected the brine upward into the ice itself through basal crevasses and fractures. The 2017 Journal of Glaciology paper describes a subhorizontal and glacial brine zone upstream from Blood Falls, and supports a model in which pressurized subglacial brine enters the ice through basal crevassing, moves toward the terminus, and is eventually released episodically as a kind of artesian pressure outlet. That hidden plumbing is one of the most quietly remarkable parts of the story. When people imagine water under a glacier, they often picture it flowing neatly along the bed, like a cold underground stream slipping under the ice. Bloodfall suggests something a little stranger. The brine is not just under the glacier, at least part of it is within the glacier, occupying an englacial zone and connected to subglacial reservoirs upstream. Researchers used radio echo sounding to identify an elongated brine-rich zone within the ice, with detectable brine extending dozens of meters laterally and likely much higher concentrations toward the center. Their interpretation was that pressurized subglacial brine is injected upward into the glacier through a network of basal crevasses, where it can remain liquid and then be carried toward the terminus. So the glacier is not merely covering the brine, it is in places containing and transporting it. There is something almost mechanical about that image, though not in a modern engineered sense, more like a natural pressure system that has had far too long to become efficient in its own odd way. The brine pools upstream. Pressure builds. Some of it is injected into fractures within the ice. Hydraulic gradients guide it toward the terminus. Moraines and cold near-surface ice block easier exits elsewhere. Then, under the right conditions, some of that pressurized fluid finds release through blood falls. The 2017 glaciology study explicitly describes blood falls as acting as a pressure release valve for the hydrologic system. That is a useful phrase because it strips away the drama of the name and replaces it with something more accurate. The glacier is not bleeding, it is venting. There is another piece of the puzzle that makes the buried brine system easier to understand, and that is the role of cryoconcentration. When saline water freezes, the forming ice excludes much of the dissolved salt, leaving the remaining liquid saltier and saltier. Over time, repeated freezing can create a residual brine that is far more concentrated than the water it started from. That process is one of the reasons researchers think ancient marine waters, or later lake waters, could have evolved into the dense brines now detected under Taylor Glacier and elsewhere in Taylor Valley. The Nature Communication study points to freezing and climatic change as likely mechanisms that built up dense brines from saline precursor waters, while the 2019 geochemistry work evaluates how marine-derived fluids could have been concentrated and altered over time. It is a slow concentrating machine, driven not by evaporation alone but by cold. Cold, in other words, is not just the thing trying to destroy the liquid system. It is also part of what made the system possible. That is one of the elegant reversals at the heart of Blood Falls. We tend to think of freezing as the enemy of flow, the moment when water becomes still and inactive. But here, freezing helps create the very salinity that allows liquid to survive later on. The glacier and the climate do not merely suppress the water, they refine it. They strip away fresh water into ice and leave behind a more concentrated residue that can persist where ordinary water cannot. It is a bit like a long, geological process of reduction, the landscape slowly removing everything too fragile to remain liquid until only the stubbornest chemical form is left. And that stubborn fluid has consequences beyond the spectacle of the outflow, because the brine system beneath Taylor Glacier is not isolated from the rest of Taylor Valley. Geophysical evidence suggests broader subsurface hydrological connections in the dry valleys, including between lakes once thought isolated. In the Bonny Basin specifically, the subglacial brine under Taylor Glacier appears connected to the west lobe of Lake Bonny, and other studies have found year-round evidence of cold brine intrusions into the lake from beneath the glacier face, even excluding surface input from Blood Falls itself. So the ancient brine is not just sitting under the glacier as a curiosity, it is part of the chemical life of the valley, feeding nutrients and unusual dissolved constituents into nearby waters. It also means that Blood Falls is only the public-facing part of a much larger hidden environment. The red outflow is famous because it is visible, but the actual brine system is bigger, darker, older, and less photogenic. There are no dramatic postcards of brine-saturated sediments under hundreds of meters of ice. There is just a stubborn body of conductive salty water and sediment, shaped by ancient marine incursion, glacial advance, freezing, concentration, rock chemistry, and time. A lot of time. Enough time that the glacier we see now is really just the latest lid on a much older story below it. And perhaps that is the best way to picture the ancient brine beneath Taylor Glacier. Not as a little hidden lake with a horror movie name attached to it, but as a buried memory of a very different valley, preserved and modified beneath ice. Long ago, this was a landscape with marine influence and later large paleo lakes. Then the climate shifted, glaciers advanced and retreated, salts concentrated, dense fluids sank into permeable sediments, and the lower glacier eventually overrode and sealed parts of that system. What remains is not a snapshot from one moment, but the chemical residue of many moments layered together. The brine is ancient, but not frozen in time. It has been reacting, moving, and waiting. Which makes the next step in the story even stranger, because once you accept that this salty, iron-rich fluid has persisted beneath the glacier for immense stretches of time, another question becomes impossible to ignore. A hidden brine system is already unusual. A hidden brine system in darkness, with almost no oxygen under crushing cold and pressure, would seem like the sort of place where nothing much should be alive at all. And yet that assumption, like so many others in Taylor Valley, turns out not to survive first contact with the evidence. Once you understand that Blood Falls is being fed by ancient brine rather than ordinary meltwater, the place changes again. It is no longer just a red outflow in a cold desert. It becomes the visible edge of a hidden environment, a world below the glacier that has been cut off from sunlight for a very long time. The likely fluid source identified in the classic science paper was a pool of marine-derived brine trapped about 4 kilometers upstream from the glacier snout beneath roughly 400 meters of ice, and the authors argued that the brine had been isolated for at least 1.5 million years. NASA's astrobiology program later summarized the same setting in very direct terms: cold, dark, and lacking oxygen. That last detail is what gives this place its particular weight. Plenty of places on Earth are dark at night. Plenty are dark underground. Plenty are dark in winter. But the hidden environment feeding Blood Falls is not dark in that ordinary everyday sense. It is dark because it sits under hundreds of meters of ice. There is no dawn down there, no dusk, no blue twilight, no thin summer glow slipping through the weather. A human being can adjust to low light, eyes widen, pupils open, shapes return. But there is no adjusting to total burial beneath a glacier. Sunlight is not dimmed, it is excluded. The source region exists beyond the reach of photosynthesis not because the season is wrong or the weather is poor, but because the entire habitat is sealed under ice thick enough to keep the surface world physically and chemically at a distance. That has immediate consequences for how this hidden world works. On the surface of Earth, most ecosystems ultimately run on sunlight. Plants, algae, and photosynthetic microbes capture light energy, turn carbon dioxide into organic matter, and form the base of food webs that then support everything else. Even animals that never see a leaf are still, in the end, living off an economy built by sunlight. But beneath Taylor Glacier, that route is cut off. The source brine is isolated from light, sealed off from easy atmospheric exchange, and chemically very different from ordinary fresh water. The 2009 science study found no dissolved oxygen in the outflowing brine and reported that more than 97% of the dissolved iron was present as Fe2, both signs of a reducing oxygen-poor environment. In such a place, if anything is going to persist, it has to rely on chemistry instead of light. That is one of the most important shifts in perspective Bloodfalls offers. It asks you to stop thinking of habitability in the familiar surface sense. No sunlight, no open water, no visible plants, no breathable oxygen, no obvious source of fresh incoming nutrients. To most of us, that sounds less like a habitat and more like a storage problem. But microbes do not negotiate with the world using our assumptions. They do not require scenery, weather, or a sensible travel brochure. They need liquid water, a source of energy, useful chemistry, and enough time to adapt. Brines enlarge the range of conditions in which liquid water can remain stable, because salts lower freezing temperatures and help water stay liquid below zero. NASA's astrobiology strategy points to Bloodfalls as a particularly useful example of sulfur and iron cycling microbial communities in hypersaline habitats operating in the absence of sunlight. In other words, the hidden world below Taylor Glacier is dark, but it is not chemically empty. There is something counterintuitive about that if your intuition has been trained mostly by surface life. We tend to imagine darkness as a shortage. No light means no energy. No oxygen means no possibility. No fresh inputs mean no future. But geochemistry does not care about our surface prejudices. If water stays liquid, salts remain dissolved, minerals interact with that water, and gradients exist between one chemical state and another, then energy can still be available. Not the fast, generous flood of sunlight falling over a forest or a lake, but enough. Enough for a sparse, slow system. Enough for organisms that do not ask for much, except continuity. The science paper on Bloodfalls described a metabolically active microbial assemblage in the anoxic iron-rich brine, and found evidence consistent with active sulfur cycling. That is a remarkable sentence once you let it settle properly. Not ancient, dead residues. Not a sterile, preserved fluid. Active metabolism in a place sealed under ice for geological time. The hidden world under Taylor Glacier is also old in a way that surface environments often are not. On the surface, weather and biology keep rearranging things. Water flows in, organisms bloom and die, sunlight drives daily and seasonal rhythms, and gases move constantly between air, water, and soil. Beneath the glacier, by contrast, time behaves differently. The science study reported radiocarbon data showing that the dissolved inorganic carbon in the Bloodfalls brine is very old, and the broader literature describes the source region as a long isolated subglacial or englacial brine system with marine roots. This gives the place the quality of a time capsule, though not a perfectly untouched one. It has not simply sat there doing nothing. Chemistry has continued. Fluids have remained mobile. Pressure has built and released. But the outside world has not been dropping in fresh light, fresh oxygen, and fresh, easy energy every morning. That long isolation matters because it changes the scale of the question. If you ask whether a burst of life can briefly survive in a harsh place, the answer is often yes. Microbes can be surprisingly tough over short intervals, but Bloodfalls pushes us toward a harder version of the question. What can persist in a dark, cold, oxygen-poor brine for hundreds of thousands or even more than 1 million years of isolation? That is a much sterner test. A weekend in bad conditions proves resilience. Geological isolation proves that an ecosystem has found a workable arrangement with its environment. The NASA astrobiology summary emphasized that the microbes associated with Bloodfalls appear to have adapted over roughly 1.5 million years to manipulate sulfur and iron compounds in order to survive. That does not sound like a temporary emergency response. It sounds like a way of life, and the physical layout of the system only adds to the sense of removal. The likely source lies under thick ice, upstream from the visible outflow, with hidden pathways routing brine through or beneath the glacier before it reaches Bloodfalls. Later, glaciological work mapped an englacial brine zone within Taylor Glacier itself, and described Bloodfalls as a pressure release valve for that hydrologic system. So when we speak of a hidden world without sunlight, we are not talking about one neat, underground chamber. We're talking about an environment built from buried liquid, saturated sediments, pressurized pathways, fractures in cold ice, and a chemical regime that remains distinct from the bright oxygenated surface above. It is less like a cave and more like a concealed network. The absence of oxygen is just as important as the absence of light. For larger animals like us, oxygen feels almost synonymous with livability. We notice the slightest shortage quickly and unhappily. But in the Bloodfall's brine, dissolved oxygen was not detected, and the chemistry points to a reduced environment where iron remains largely in the ferrous state until the brine reaches the surface. That means the hidden source region operates according to rules very different from surface waters exposed to air. Oxidizing conditions do not dominate below the glacier. Instead, reduced compounds can accumulate and persist. That is why the clear brine can emerge, and only then, at the surface, turn dramatically red as its iron meets oxygen. The surface spectacle is the mark of a subsurface environment that stayed out of contact with oxygen long enough to keep that iron reduced. This is one of those cases where chemistry and atmosphere are really telling the same story from different angles. No sunlight means no photosynthesis. No oxygen means no easy reliance on the kind of respiration most people associate with life. The result is not necessarily lifelessness. Instead, it is a narrower and more specialized set of options, and nature is very good at exploiting narrow options for very long periods if the system is stable enough. The Bloodfall's brine contains sulfate, ammonium, dissolved inorganic carbon, dissolved organic carbon, and a large amount of dissolved iron, all of which matter because they tell us the fluid is not blank water but a chemically structured environment. There are materials there to react, recycle, and support metabolism. The environment is harsh, yes, but not empty, and that may be the most useful correction Bloodfalls offers to the imagination. We often confuse extreme with barren. Sometimes that is fair. Plenty of environments really are close to sterile, but sometimes an extreme environment is simply selective. It strips away the easy options and leaves only the difficult ones. The hidden brine world under Taylor Glacier appears to be one of those places. The conditions are so constrained that only a very limited kind of ecosystem can operate there, yet that ecosystem appears to have remained metabolically active rather than merely preserved. The science paper explicitly framed subglacial environments as a largely unexplored component of Earth's biosphere, and Bloodfalls gave researchers unusual access to one of them, without having to drill blindly into an intact Antarctic ice sheet. It is hard not to notice how much this setting resembles the sort of environment people speculate about when they talk about life elsewhere. That comparison is not a journalistic flourish added afterward because it sounds futuristic. NASA's own astrobiology strategy uses Bloodfalls and related brine habitats as examples of how life can persist in hypersaline aqueous environments without sunlight, precisely because such systems help define the outer limits of habitability. The report notes that examining these communities expands the known limits of life and highlights Bloodfalls as relevant to understanding potentially habitable environments on other worlds, especially cold ones where salts might allow liquid brines to survive in cracks, crevasses, or subsurface pockets. That does not mean Taylor Glacier is secretly Europa with worse logistics, but it does mean the hidden world beneath it is scientifically useful in a very broad way. If life can persist in dark, sub-zero, hypersaline, oxygen-poor systems on Earth, then our sense of where to look for life elsewhere has to widen. Bloodfalls is not just a curiosity about one Antarctic glacier. It is a reminder that habitable does not have to mean sunny, temperate, and obvious. It can also mean buried, saline, and chemically alive in ways that are easy to miss from the surface. That is why the place matters well beyond Antarctica. It gives researchers a natural example of a habitat powered by rock-water chemistry rather than daylight. There is also a more terrestrial lesson in it. Even on Earth, we tend to overestimate how much of the planet's living story is happening where we can see it. Forests, reefs, grasslands, lakes and coastlines are visually persuasive, so we treat them as the main stage. But the biosphere extends into less obvious places. Deep sediments, crustal fluids, hydrothermal systems, buried aquifers, sea ice channels, and subglacial waters. Bloodfalls belongs to that less visible Earth. The world beneath Taylor Glacier is not dramatic because it is full of large things. It is dramatic because it shows how much can happen in small, hidden, chemically disciplined spaces. A glacier that looks silent from the outside may still be sheltering an entire set of reactions and living strategies below. Another striking feature of this hidden environment is that it does not receive the ordinary signals that structure most surface ecosystems. There is no day-night cycle in the source region, no sun angle changing through the season in any meaningful biological sense, no sudden rainstorm delivering fresh oxygen and nutrients, no breeze mixing the water, no birds dropping in with stray bits of organic material. Whatever happens, there has to be built from what the system already contains and what its own internal hydrology can redistribute. That makes it feel closed, almost self-referential. Yet it is not completely static, because Bloodfalls itself proves that some part of this world still connects outward through episodic discharge. The hidden environment is sealed enough to preserve unusual conditions, but not so sealed that it has stopped moving altogether. That partial connection may be one reason the place is so conceptually rich. Entirely sealed environments are easy to romanticize and hard to study. Entirely open environments are easy to sample but easy to disturb and dilute. Bloodfall sits in between. It offers access without total exposure. The outflow gives researchers a chance to study chemistry and life from below the glacier without drilling straight into the deepest source at first pass. That is part of why it became such a compelling target for microbiologists and geochemists. It is a leak from a hidden world, which is a far more convenient scientific arrangement than a hidden world with perfect manners. And perhaps that is the best way to think about the darkness below Taylor Glacier, not as empty blackness, and not as a horror film setting waiting for dramatic music, but as a long isolated working environment where the usual surface rules are suspended. No sunlight, no oxygen to speak of, no obvious external food chain, no easy exchange with the atmosphere, and still the system persists. The brine remains liquid because salt lowers its freezing point. The chemistry remains reduced because oxygen is absent. Iron and sulfur remain central because they can participate in energy-yielding reactions when light cannot. Over long timescales, the glacier becomes not just a lid but a filter, blocking most of the surface world while preserving a habitat of its own kind beneath. Once you accept that, the next step becomes unavoidable. A hidden world without sunlight is already strange enough. A hidden world without sunlight that still supports active life is stranger still, and that is where the story naturally goes next, because once the darkness is understood, the real question is no longer whether the environment is severe. It is what, exactly, has been living in that dark brine all this time, and how those microbes managed to make a living where almost every ordinary source of biological comfort has been removed. If the hidden world beneath Taylor Glacier is the stage, then the microbes are the reason the story stops being a geological curiosity and becomes something much larger. Saltwater under ice is interesting on its own. Ancient saltwater under ice is more interesting. Ancient saltwater under ice that still supports living cells in darkness, with no photosynthesis and effectively no oxygen, is the point where most people begin to revise their assumptions about what counts as a habitable place. The key thing to understand is that scientists did not just find chemical hints and decide to imagine life into the gap. They found evidence of a metabolically active microbial assemblage in the Bloodfall's brine itself. The 2009 science paper described the system as a sulfate-rich, ancient marine brine beneath Taylor Glacier hosting an active microbial community, and it argued that this community maintains a ferrous, iron-rich subglacial environment through sulfur cycling under conditions of limited organic carbon and no contemporary photosynthesis. That phrase metabolically active is doing the important work. It means these microbes are not just preserved bodies sitting in cold brine like a forgotten sample in the back of a freezer. They are not fossils with excellent timing. They are alive in the only way microbes ever prove they are alive, by using chemistry, maintaining cells, and participating in cycles that alter the composition of their environment. In the bloodfall system, researchers connected the microbial community to sulfur transformations, and to the unusual persistence of ferrous iron in the brine. The science paper specifically proposed that a microbial consortium facilitates a catalytic sulfur cycle, with ferric iron acting as the terminal electron acceptor, and that this helps explain why the subglacial brine stays chemically reduced and rich in Fe2 despite the presence of sulfate. It helps here to slow down and translate the basic idea into ordinary language. On the surface of Earth, many living things ultimately get their energy from sunlight, either directly through photosynthesis or indirectly by eating something that did. Below Taylor Glacier, that option is off the table. There is no light. So the microbes living in the bloodfall system are not using sunlight as their main power source. Instead, they appear to rely on chemical energy, especially from transformations involving sulfur and iron. NASA's astrobiology materials summarize bloodfalls as an example of sulfur and iron cycling microbial communities thriving in hypersaline conditions without sunlight, and the original science study tied the brine chemistry to microbial sulfur cycling under anoxic conditions. This is chemotrophic life, built not around light but around chemical gradients and redox reactions. That already sounds impressive enough, but the details make it better. One of the early clues came from gene-based evidence. The 2009 paper reported analysis of adenosine 5' phosphosulfate reductase genes, usually called APS reductase genes, which are associated with microbial sulfur metabolism. Most of the APS genes detected in bloodfalls grouped with known dissimilatory and sulfur disproportionating species, and the authors concluded that the genetic evidence, together with isotopic evidence, was consistent with active sulfur cycling in the brine. Put less formally, the microbes were not just floating there politely, they were carrying the molecular tools needed to make sulfur chemistry part of everyday life in that dark subglacial system. There is also a nice bit of scientific patience built into this story. Researchers did not arrive with a neat cartoon version of the ecosystem and find that reality matched it perfectly. In fact, bloodfalls presented them with something slightly awkward. The brine contained sulfate, but they did not find the obvious large accumulation of sulfide that a simpler version of sulfate reduction might lead you to expect. The sulfur isotopes and gene evidence suggested partial sulfate turnover and a more intricate sulfur cycle than a straightforward one-way reduction to sulfide and burial. The authors argued that the system showed sulfur cycling without significant sulfur loss to pyrite, and that this helps explain why the environment remains rich in electron acceptors while still being anaerobic. In other words, the microbes appear to be running a chemical economy that is cleverer than the first rough sketch. This is where bloodfalls becomes a very good reminder that microbial life is usually less cinematic and more ingenious than people expect. If you ask a human to survive in a buried Antarctic brine for geological timescales, the human will sensibly decline. If you ask a microbe, the answer is more likely to be, what exactly are the salts, what are the redox couples, and how much time do I get? The microbes associated with bloodfalls seem to have found a workable arrangement using the materials available: sulfate, iron, some organic carbon, and a stable liquid habitat maintained by high salinity. NASA's Earth Observatory description of bloodfalls notes that the ecosystem has persisted in darkness and with little to no oxygen, with microbes adapting by using sulfate and iron compounds to survive, rather than relying on sunlight-driven production. What kind of microbes are we talking about? Early diversity work showed that this community had a distinctly marine flavour. which makes sense if the brine itself has marine origins. A 2007 study reported that 74% of clones and isolates from bloodfalls shared high 16SRR-NA gene sequence homology with phylotypes from marine systems, and the clone library was heavily dominated by a phylotype with 99% sequence identity to Thiomicrospira arctica, a psychrophilic marine autotrophic sulfur oxidizer. Other phylotypes were related to beta, delta, and gamma proteobacteria. That is the sort of result that sounds very technical until you translate it into a simple picture. The subglacial microbial community looked much more like something with a marine ancestry than like a random assortment scraped in from surrounding dry valley soils. That marine signature matters for another reason as well. It suggests continuity. The microbes below Taylor Glacier were not just invented by the glacier after the valley froze over. They appear to be tied to the long history of the brine itself, which most evidence connects to marine waters that were later cryoconcentrated and altered beneath advancing ice and changing climate. So when scientists describe the bloodfall's microbial assemblage as largely marine, they are not just naming a taxonomic pattern, they are also pointing to the history of the habitat. These microbes seem to belong to the same buried story as the brine, the salts, and the chemical evolution of the valley. The fluid is ancient, and the biology seems to remember that. It is tempting at this point to imagine the hidden ecosystem as bustling, but that would be the wrong scale entirely. This is not a crowded tropical reef under ice. It is a sparse, energy-limited microbial world. The science paper estimated a doubling time for heterotrophs in the bloodfall system of roughly 300 days. That is a useful number because it forces the imagination to slow down. These organisms are not racing through generations every afternoon. They are operating on a schedule that makes a houseplant look impatient. And yet over 1.5 million years of isolation, even slow growth accumulates into an extraordinary amount of persistence. The authors calculated that such a doubling time would still correspond to roughly 1 million generations over that span. Slow is not the same thing as inactive. In microbial terms, slow can still be very much alive. That slow pace also explains why the chemistry and the biology are so tightly braided together here. In a rich environment with lots of energy and constant inputs, many pathways can coexist without the whole system becoming easy to read. In bloodfalls, everything has to count. There is limited organic carbon, no contemporary photosynthesis, no dissolved oxygen, and a heavy dependence on what the environment itself can provide. The 2009 study framed the brine as paradoxically rich in electron acceptors relative to electron donors despite being anaerobic, and argued that the microbial sulfur cycle helped maintain the unusual ferrous chemistry of the system. This means the microbes are not merely adapting to a pre-existing setting. They are part of what keeps that setting the way it is. They are residents, yes, but also maintenance staff. Another reason the bloodfall's microbes matter is methodological. Subglacial ecosystems are famously hard to study without contamination, expense, and a great deal of patience. Drill too aggressively and you risk introducing surface microbes or disturbing the chemical conditions you wanted to understand. Bloodfalls offers something rare, a natural outflow from an otherwise hidden environment. The brine that seeps from the glacier gives researchers access to subglacial or inglacial material without requiring them to invent the entire access route from scratch. NASA's astrobiology coverage explicitly points out that scientists have taken advantage of these natural seep locations to study subglacial environments, and later work using the ice mole melting probe even allowed clean sampling of brine from inside the glacier before it interacted with outside air. That last point is crucial, because once the brine emerges at bloodfalls it begins changing immediately. Oxygen from the atmosphere alters the ion chemistry and turns the outflow red. If you want to know what the microbes are actually living with below the glacier, it helps to sample the fluid before the surface gets involved and starts redecorating everything in rusty shades. NASA notes that researchers were able to penetrate the glacier and collect glacial brine, before it had contact with outside air, which gives a much better picture of the native sub-ice environment. That is scientifically important because many microbial metabolisms are exquisitely sensitive to oxygen, redox state, and the balance of dissolved compounds. Sampling after surface exposure is a bit like trying to understand a quiet person by observing them only at a surprise party. There is also a wider ecological point hiding in all this. The microbes of blood falls do not just tell us that life can exist in harsh conditions. That is already a very broad statement, and by now most people know extremophils are good at making our mental boundaries look silly. Blood falls tells us something more specific. It shows that an ecosystem can remain metabolically active in cold, hypersaline, oxygen-poor darkness for enormous spans of time, provided there is a stable liquid habitat and usable chemistry. NASA's astrobiology strategy highlights blood falls precisely because sulfur, methane, and ion cycling in such lightless brine habitats expands the known limits of life and helps define what might count as habitable, beyond the easy surface settings we usually picture. And that is why people in astrobiology keep coming back to this place. Blood falls is not just weird Antarctic scenery. It is a working demonstration that life can live on chemistry alone in a buried icy environment. The NASA strategy document specifically identifies the blood falls microbial community as relevant to habitability on other worlds, because similar brine channels, inclusions or subsurface salty reservoirs might exist in icy environments elsewhere in the solar system. The lesson is not that Mars or Europa must have life because Antarctica does. The lesson is more disciplined than that. It is that Earth contains at least one real example of a dark, cold brine habitat where sulfur and iron-based microbial processes support persistence without sunlight. That makes the idea of analogous habitats elsewhere more scientifically serious than it would otherwise be. There is a quieter implication too, and it concerns Earth's own past. The science paper explicitly linked the bloodfall system to the question of how Fe2-rich waters might accumulate even in the presence of an active sulfur cycle during times of diminished net photosynthesis, such as Neoproterozoic snowball Earth episodes. In that sense, the microbes beneath Taylor Glacier are not only interesting because they resemble the sort of life we might seek elsewhere, they are also interesting because they may resemble strategies that mattered during some of the most severe climatic intervals in our own planet's history. When Earth itself was far less welcoming than usual, ecosystems powered by minimal organic input and chemical cycling, rather than abundant sunlight, may have been much more important than the surface world would suggest. For all that, it is worth resisting one very common urge, which is to turn the bloodfalls microbes into miracle creatures. They are not magical, and the science is stronger when we do not pretend they are. They are microbes doing what microbes do best, finding a narrow way through a bad situation, and then sticking with it for a very long time. Their environment is harsh, but it is not random. It has liquid water because the salts are high. It has chemical energy because reduced and oxidized compounds can still interact through microbial processes. It has stability because the glacier above it has sealed and protected the system over long timescales. The microbes are remarkable, but they are remarkable in a very microbial way, through patience, versatility, and biochemical opportunism rather than showmanship. Even the cast of likely players reflects that practical style. Early work pointed to sulfur oxidizes and other marine-related bacteria, while later sampling and cultivation from the Taylor Glacier brine identified cold-loving, salt-tolerant organisms, including a Marinobacter strain from the englacial brine. DOE Joint Genome Institute material on the bloodfalls ecosystem described sequencing efforts aimed at understanding how such bacteria tolerate cold and what organic material they can use in an environment that does not allow photosynthesis. So the picture is not of one lonely superbug doing everything alone. It is a community with overlapping roles tied together by sulfur, iron, carbon, and the very limited menu the glacier allows. That community quality matters because ecosystems, even tiny ones, are rarely one organism stories. One lineage may oxidize sulfur, another may reduce a sulfur compound, another may handle organic leftovers, another may interact with iron in a way that shapes what remains dissolved. The 2020 Bloodfall's plume work reported that sulfur cycling metabolisms appear to be used across a wider range of bacterial taxa than previously predicted, describing microbial metabolic redundancy as a key mechanism in this Antarctic subglacial environment. That is exactly the sort of result you might expect in a system where failure is not a desirable experiment. If only one microbe could do an essential job, the whole community would be fragile. If several can, the ecosystem becomes more resilient even while remaining sparse. So the microbes living in the frozen dark are not an ornamental detail added to the Bloodfall story for extra wonder. They are one of the central reasons the place matters. They show that beneath Taylor Glacier there is not just chemistry but ecology, not just preserved fluid but an active system, not just isolation but survival. And because they live by methods that differ so sharply from the sunlit biology most people know, they force the whole landscape to be reinterpreted. The glacier is not simply covering ancient water, it is sheltering a chemical habitat with its own long-running microbial economy, one that stayed out of sight until the brine found a way to seep out and betray what was happening below. Which is why, once scientists realised that the red outflow was carrying evidence of living processes, the next problem became unavoidable. How exactly do you prove all of this in a place that is buried, cold, episodic, and determined to make every answer difficult? What makes the Bloodfall story satisfying is that it was not solved in a single dramatic moment by one person standing on the ice and announcing the answer like a detective at the end of a novel. It took more than a century, and the solution arrived in pieces. The first piece was simple observation. In 1911, during the Terra Nova expedition, Thomas Griffith Taylor saw a red outflow at the snout of the glacier that now bears his name. At the time, the colour was initially attributed to red algae, which was a reasonable enough guess when all anyone had was a startling visual problem and not much else. Bloodfalls entered science not as a solved phenomenon, but as a very good question in an inconvenient place. That is often how these mysteries begin. The earliest explanation is usually not foolish, is just working with limited tools. If you see something red on ice, especially in the early 20th century, biology is an obvious place to start. Later researchers then revised the picture and connected the stain more firmly to iron-bearing material rather than algae, but even that did not finish the job. For decades, the broad idea was that iron oxides were involved, yet the exact nature of the red material, the source of the liquid, and the reason the outflow happened at all remained incomplete. Bloodfalls was one of those scientific problems that looked half solved for a long time, because people understood bits of it while the deeper structure stayed hidden. The first real leap forward came when scientists stopped treating bloodfalls as mainly a colour puzzle and started treating it as a chemical system. That shift matters. If all you ask is, why is the glacier red, you get one kind of answer. If you ask, what kind of liquid is coming out, what is dissolved in it, how old is it, and what happens to it before and after it reaches the air, then the entire problem opens up. By 2009, work led by Jill McCookie and colleagues showed that the outflow was coming from an ancient, oxygen-poor brine system below the glacier. Their science paper reported no dissolved oxygen in the brine, found that more than 97% of the iron was present as Fe2, and described the environment as a subglacial habitat supporting metabolically active microbes. It also noted that salts and iron minerals precipitate rapidly when the fluid meets the oxidizing atmosphere, which immediately tied the visible red staining to a change that happens at the surface rather than to some naturally crimson fluid waiting below. That 2009 work also changed the tone of the mystery, because it showed that Bloodfalls was not simply a geological oddity, it was a living geochemical system. The brine had old dissolved inorganic carbon, carried abundant dissolved iron, sulfate, chloride, and ammonium, and contained a microbial community using sulfur chemistry in the absence of sunlight and oxygen. In other words, the outflow was not a random red leak. It was evidence of a buried subglacial environment with chemistry and biology of its own. Once that became clear, scientists were no longer asking only why the surface looked strange. They were asking what lay beneath the glacier, how that hidden environment stayed liquid, how it remained connected to the surface, and how large the concealed system might be. Even then, there was still a major problem. Knowing that the brine was ancient and chemically unusual did not tell researchers exactly where it was, how extensive it was, or by what route it reached bloodfalls. A century-old mystery can survive quite comfortably if the critical parts remain buried under hundreds of meters of Antarctic ice. So the next stage in solving the problem depended not on one clever sample bottle, but on better ways to see through the glacier and into the valley subsurface. That is where geophysics entered the story in a much bigger way. In 2015, airborne electromagnetic surveys over Taylor Valley produced regional-scale resistivity data showing extensive conductive brine systems beneath parts of the McMurdo Dry Valleys. The study concluded that bloodfalls is fed not by a tiny isolated pocket near the glacier front, but by a more regionally extensive body of subglacial brine. That was a major shift in scale. The outflow was not a local stain with a local cause. It was the visible expression of a buried groundwater system. That airborne electromagnetic work is a good example of science solving a mystery by changing the question from what is at this one weird spot to what is the whole hidden system around this weird spot. Conductive fluids such as brines behave differently from ice and dry permafrost in resistivity surveys, so researchers could use airborne instruments to map zones where something much saltier and more liquid was present below the surface. The 2015 Nature Communications paper described two extensive subsurface brine systems in the dry valleys and argued that bloodfalls discharges are sourced from a larger subglacial body rather than a small feature confined to the glacier terminus. That mattered because it turned bloodfalls from an isolated curiosity into a hydrological clue about the valley as a whole. Still, scientists wanted more than a broad subsurface map. They needed to understand how the brine actually travelled through or beneath Taylor Glacier. A regional brine source is one thing, a flow pathway is another. In 2017, researchers used radio echo sounding to image a sub-horizontal zone of englacial brine upstream from bloodfalls. Their Journal of Glaciology paper reported detectable brine extending laterally away from the central axis of that zone, and inferred a network of basal crevasses that allowed pressurized subglacial brine to be injected upward into the glacier. The study concluded that Taylor Glacier hosts an active englacial hydrologic system feeding bloodfalls, even though the glacier sits in a very cold, low-melt environment where such a system would not normally be expected. This was a very important moment in the mystery because it solved something people often do not notice at first. Bloodfalls is not just strange because the water is red. It is strange because water is moving through a glacier that, by ordinary expectations, ought to be too cold to support that kind of persistent internal hydrology. The 2017 study showed how the glacier gets around that problem. Elevated salt content lowers the freezing point of the brine, and latent heat released during freezing helps keep the fluid pathway active. In the researchers' model, pressurized brine is injected into the ice, routed toward the terminus by hydraulic gradients, and eventually released at bloodfalls. So by this point, scientists had moved from something red comes out of the glacier to a physically coherent description of buried brine, flow pathways, and pressure-driven transport within the glacier itself. Even with all that progress, one part of the visual mystery still lingered. Scientists broadly knew that iron was involved in the red colour, and for years the short version was that the brine rusts when it reaches the air. That explanation works well enough for a first pass, but it was not fully resolving what the red solids actually were. Earlier descriptions had leaned on iron oxides and hydroxides in a fairly general sense, but the detailed mineralogy was missing. Then a newer generation of tools pushed the problem down to a much finer scale. A multi-technique analysis published in Frontiers, along with microscopy work highlighted by Johns Hopkins in 2023, found that the surface materials from blood falls contain abundant iron-rich amorphous nanospheres, rather than strong evidence for the expected crystalline iron oxide or hydroxide phases. The study concluded that the red colour arises when dissolved iron, in the subglacial fluid oxidizes upon exposure to air and forms nanospheres of amorphous hydroxylated mixed valent iron-containing material, with colour also influenced by other ions. That may sound like a very technical refinement, but it is actually one of the nicest examples of how scientific tools change answers. Earlier work was not wildly wrong to connect blood falls to iron oxidation. It just did not have the right resolution to see exactly what form the iron-rich solids were taking. Johns Hopkins researcher Ken Livy used transmission electron microscopy to examine solids in blood fall samples and found tiny nanospheres that previous, more conventional methods had not pinned down. The clearer picture was that the fluid emerges clear and then rapidly turns crimson, because the dissolved iron transforms into these tiny oxidized particles after exposure to air. The final visual effect had been hiding in plain sight, but only because the key materials were too small and too structurally unusual to be neatly captured by older assumptions. That is a lovely scientific pattern, really. First, a mystery seems mysterious because no one can see enough. Then it remains mysterious because everyone thinks they already see enough. Blood falls lived in that second stage for quite a while. People knew iron mattered, so the red colour felt more or less explained, but the more exact answer had to wait for instruments capable of resolving amorphous nanoscale material rather than just familiar crystalline minerals. The Frontiers paper even notes that there is no strong evidence for crystalline iron oxide or hydroxide phases dominating the samples, and that the red colour is not entirely captured by the old idea of ordinary iron, hydroxides. That is not science reversing itself so much as science sharpening itself. And then, just when the chemistry looked much cleaner, another practical question remained. Scientists knew what the brine was. They had mapped a larger buried source. They had identified pathways through the glacier. They had refined the explanation for the red colour. But blood falls itself is episodic. It does not simply pour out every moment at a constant rate like a polite little spring. So what actually triggers a release event? Why does the glacier vent this brine when it does? That turned out to require not one grand expedition, but a fortunate cluster of instruments recording the right things at the right time. A 2026 Antarctic Science note reported a serendipitous alignment of observations from September 2018. Continuous GPS data from the glacier surface, a time-lapse camera aimed at blood falls, and thermistor strings in the nearby west lobe of Lake Bonny, all recorded simultaneously during an outflow event. The researchers observed an approximately 15mm downward drop of Taylor Glacier that coincided with blood falls discharge and a cold anomaly in the lake. That is not a huge drop by everyday standards, but it is enough to matter when you're dealing with the mechanics of pressurized fluid under ice. The 2026 paper interpreted the event as further evidence that the weight and movement of the overlying glacier help drive subglacial brine expulsion. In other words, the glacier itself appears to squeeze and release the system. The brine is not merely sitting there and occasionally deciding to make an entrance. Pressure changes in the glacier, and the subglacial plumbing seem to help force it outward. This is the kind of result that would have been very hard to produce in 1911, very hard in 1965, and still difficult even in 2009. It depended on years accumulated understanding plus modern instruments quietly waiting for the right event to happen. That is why saying scientists solved bloodfalls is accurate but slightly misleading if you imagine a single moment of triumph. What they actually solved was a layered puzzle, and each layer needed its own method. Field observation established the phenomenon. Chemistry showed the brine was ancient, oxygen-poor and iron-rich. Microbiology showed the hidden system was inhabited and metabolically active. Airborne electromagnetic surveys expanded the source from a little local pool to a larger valley brine system. Radio echo sounding mapped an englacial pathway and showed how pressurized brine could move within a cold glacier. Electron microscopy refined the exact cause of the red colouring at the particle level. And synchronized GPS, thermal and imaging data linked visible discharge to glacier motion and pressure changes. It was not one key opening one lock. It was a ring of keys collected over a century. There is also something quietly encouraging about how mixed the toolkit became. Bloodfalls was not solved by one discipline claiming victory over the others. Glaciologists needed geochemists. Geochemists needed microbiologists. Microbiologists benefited from clean sampling strategies and molecular tools. Geophysicists provided the larger hidden map. Material scientists brought the nanoscale perspective that clarified the colour itself. And environmental monitoring tied episodic release to glacier behaviour. Bloodfalls is a good lesson in how modern science often works when the problem is real and awkward enough. Nature does not divide itself into departments just because universities do. The glacier did not care whether the eventual answer would be filed under chemistry, hydrology, microbiology, or planetary analogue studies. It simply kept leaking its evidence in whatever language it happened to prefer. It is also worth noticing how much of the mystery was solved by learning to trust indirect evidence. Very little about bloodfalls could be approached the way one studies a pond in a park. Researchers had to infer hidden structure from resistivity, internal pathways from radar reflections, microbial metabolism from genes and isotopes, and discharge mechanics from coincident instrument signals. That is not second-rate science. It is exactly how one studies buried or inaccessible systems with any seriousness. Bloodfalls became understandable because scientists learned to read clues properly rather than demanding that the glacier kindly expose its entire interior in one convenient afternoon. And in a way, that makes the solution more elegant than a single direct look ever would have been. There is something fitting about a hidden Antarctic system being solved through patient inference, repeated sampling, and better instruments rather than through brute force simplicity. The glacier gave up the truth in layers. First, that the red was not blood, then that it was not algae, then that the iron chemistry was subtler than ordinary rust, then that the source was larger than expected, then that the fluid path ran through a cold glacier that should not have supported it so easily. Then that release events were linked to the movement and weight of the glacier itself. Each answer made the place less supernatural and more impressive. So Antarctica's red mystery was solved the way many good scientific mysteries are solved, by refusing to settle too early. Every time an explanation looked sufficient, someone came along with a better question or a better instrument. That is why Bloodfalls now stands as more than a vivid oddity. It is a case study in how science works when the subject is remote, layered, and difficult. The answer turned out to include ancient marine-derived brine, microbial sulfur cycling, iron-rich chemistry, hidden hydrology, nanoscale particles, and glacier pressure dynamics. Not one of those elements alone was enough. Together they made the picture whole, and once the mystery is solved in that practical sense, another door opens almost immediately. Because the real reward of solving Bloodfalls is not simply that we can now point at the red stain and explain it correctly. It is that the explanation reaches backward in time. A buried marine-derived brine, iron accumulating in darkness, microbes persisting under an ice-covered world, chemistry that may echo conditions from much earlier Earth history. All of that means Bloodfalls is not only a present-day Antarctic puzzle, it is also a small working archive of the deep past, which is where the story naturally begins to widen again. What Bloodfalls reveals about Earth's deep past is not one single thing, but a stack of older worlds compressed into one visible stain. At the surface, it looks like a strange modern outflow from a glacier. Underneath that, it is evidence of an ancient brine system. Underneath that again, it is evidence that Taylor Valley itself has not always looked anything like the valley we imagine today. The geophysical and geochemical work on Bloodfalls points to a marine-derived brine that has been extensively altered through long rock-water interaction, freezing, and burial beneath Taylor Glacier, and the broader Taylor Valley record shows repeated advances and retreats of the East Antarctic ice sheet through the Pleistocene and even deeper into the late Tertiary. That means the red seep is not just telling us about present-day Antarctica. It is carrying the residue of older coastlines, older lakes, older climates, and older chemical conditions that no longer exist at the surface. One of the clearest messages from Bloodfalls is that Taylor Valley has not always been a dry polar desert. The modern valley feels stripped, cold, and inland, but multiple studies argue that in the past it had a very different relationship to the ocean. The 2015 Nature Communications study states that geological evidence indicates the McMurdo Dry Valleys were a fjord ecosystem during the Miocene, when seawater intruded Taylor Valley beyond the current extent of Taylor Glacier. The 2019 geochemistry paper adds that numerous authors have argued Taylor Valley had earlier marine flooding, and while the exact timing is debated, the chemistry of the modern brine most likely points back to ancient seawater. That matters because it means Bloodfalls is not merely an Antarctic oddity. It is one of the few places where a present-day glacier is still connected chemically to a vanished marine landscape. That in turn tells us something important about how landscapes remember. Human memory is short and weather is good at erasing obvious traces, so when a valley looks dry and glacial now, we tend to assume it has always belonged to ice and dust. Bloodfalls argues against that kind of tidy thinking. Its chemistry suggests that older waters can survive in altered form long after the coastlines, fjords, and open connections that created them have disappeared. The 2019 paper evaluates several possible origins for the brine and concludes that the original water now represented by the inglacial brine is most likely ancient seawater, later modified and cryoconcentrated. It also notes that the brine chemistry bears evidence of extended interaction with aluminosilicate minerals, meaning the fluid did not simply stay bottled, it continued reacting with the valley itself. So what emerges at Bloodfalls is not a pristine relic. It is an old fluid that has lived a long, geological life underground. That long underground life matters because it preserves the effects of climate transitions that would otherwise be hard to see in one place. Taylor Valley has experienced repeated glacial and interglacial shifts, and those swings changed lake levels, redistributed salts, and altered the paths available to water. The 2019 geochemistry paper notes that during the Pleistocene the current lakes of Taylor Valley waxed and waned with climate change, and during the last glacial maximum, a large water body known as Glacial Lake Washburn existed throughout Taylor Valley, including the Bonny Basin. As lake levels fell and waters concentrated, salts were redistributed into valley soils and deeper sediments. The same paper also references repeated proglacial lake development associated with Taylor Glacier during marine isotope stages 5A, 5C, 5E, 7, 9, and 11. In plain terms, the valley has repeatedly switched between wetter and drier, more open and more sealed, and Bloodfalls appears to preserve the chemical outcome of those long oscillations. That is why Bloodfalls is so useful to geologists and paleoclimatologists. It captures the idea that ancient environments do not always vanish cleanly. Sometimes they are trapped, concentrated, and hidden. The 2015 Airborne Electromagnetic Survey found extensive low resistivity zones in Taylor Valley consistent with subsurface brines, including a system beneath Taylor Glacier connected toward Lake Bonny. The authors specifically discuss possible geologic and climate histories leading to these brine systems, including derivation from ancient marine waters and from more recent paleo lakes. Their interpretation is not that the valley contains one simple reservoir of old seawater, but that climatic cooling, freezing, cryoconcentration, and later burial under advancing ice created dense brines that still persist below the glacier. So Bloodfalls teaches a very practical lesson about Earth history. Old waters can survive climate change not by remaining unchanged at the surface, but by being driven into the subsurface where cold, salts, and geology preserve them in a new form. It also reveals that ice sheets do not simply erase the worlds they overrun. We often imagine a glacier as a bulldozer or a lid, either scraping the surface clean or sealing it shut. Taylor Glacier clearly does some sealing, but Bloodfalls shows that burial under ice can also preserve and reorganize older environmental material rather than destroying it outright. The 2019 study notes that the likely marine-derived brine was eventually overridden by Taylor Glacier as the glacier waxed and waned with climate through the Pleistocene and perhaps earlier. The 2017 glaciology study then adds the important modern piece. Taylor Glacier now hosts an active and glacial hydrologic system that carries brine toward the terminus despite very cold conditions. Taken together, those findings suggest a long history in which glaciation first trapped and concentrated older saline waters and then continued to act as a container and transport pathway for them. That is a more complicated view of glaciation than the simple idea of ice as a blank white eraser. There is a second deep past lesson in the chemistry itself. Bloodfalls is rich in dissolved iron and operates under reducing oxygen-poor conditions below the glacier. That matters because ancient Earth was not always an oxygen-rich planet. Before and during key intervals of Earth history, especially in the Precambrian, large parts of the oceans and subsurface environments were chemically very different from the modern, well-oxygenated surface world many of us implicitly take as normal. The Bloodfall system does not recreate the whole ancient Earth, of course, but it does provide a living example of an iron-rich, low-oxygen environment where microbial activity and geochemistry are tightly coupled. The 2009 Bloodfalls work, as summarised in later geochemistry and NASA astrobiology materials, showed an anoxic, iron-rich brine hosting active microbial processes, and the 2019 geochemistry paper emphasises that one of the motivating questions for subglacial systems is how they inform models for the development of life on Earth and elsewhere. Inference is required here, but it is a grounded one. Environments like Bloodfalls help scientists think about what microbial life might have looked like in earlier, darker, more chemically reduced phases of Earth history. That is especially important because modern life can distort our sense of what is normal. We live on a planet where sunlight, oxygen, and surface productivity dominate the parts of the biosphere we notice most easily. Bloodfalls reminds us that this is only one version of Earth, and not even the oldest one. The microbial life in the Bloodfall system persists in darkness, without contemporary photosynthesis, and in a brine whose chemistry is controlled by sulfur and iron cycling, rather than sunlight-driven food webs. NASA's astrobiology reporting describes the environment as cold, dark, and lacking oxygen, while the broader astrobiology framing explicitly highlights Bloodfalls as a terrestrial analogue for studying habitability and biosignature preservation in lightless brine systems. When applied back to Earth's own past, the implication is straightforward. If a metabolically active ecosystem can persist in such a place now, then ancient Earth likely hosted more chemically powered hidden habitats than the visible fossil record alone might suggest. Bloodfalls also forces a more careful view of time. We often talk about ancient Earth as if it consisted of a sequence of cleanly separated worlds. Ocean world, snowball world, oxygenated world, glacial world. Real Earth history is less neat than that. Fluids persist across transitions, salts get concentrated and redissolved. Ice advances over older deposits and later retreats. Lake basins fill, evaporate, refill, and leave chemical fingerprints behind. The 2019 paper makes exactly this sort of point by considering multiple origins and evolutionary pathways for the brine system, including cryoconcentration of past proglacial lake waters, modification and cryoconcentration of ancient seawater, and rejecting simple evaporate dissolution as the sole source. What Blood Falls gives us, then, is not a single ancient snapshot, but a long blended archive. It is a reminder that Earth history often survives not as a photograph, but as a chemically rewritten manuscript. Another thing it reveals about the deep past is how much of Earth's history may be hidden in groundwater, rather than written only in exposed rock. We're used to deep time being taught through cliffs, fossils, and sedimentary layers, all things you can point to on a field trip. Blood Falls shifts that emphasis underground. The 2015 Resistivity Survey describes extensive subsurface brine systems beneath Taylor Valley, and argues that Blood Falls is the only known surface manifestation of broader deep groundwater conditions in the dry valleys. That matters because it suggests ancient environmental information can be preserved in fluids and fluid-saturated sediments, as well as in hard rock records. If that is true in Antarctica, it is likely true in many other places too, though usually without the courtesy of a bright red leak to tell us where to look. There is also a lesson here about persistence during cold intervals. I want to be careful with this point because Blood Falls is not a direct window into every globally icy episode in Earth history, and scientists do not treat it as a perfect one-to-one replay of any specific ancient event. But as an inference, it is a strong one. A system like this shows that long-lived microbial refugees can exist beneath ice, in salty, dark, chemically active waters. The 2009 work demonstrated active life in an anoxic subglacial brine, and later NASA astrobiology materials treat Blood Falls as an environment that expands the known limits of habitability. That makes it a useful model for thinking about how microbial life on Earth might have endured through severe glacial phases, not necessarily on the surface, but in hidden saline pockets, sediments, and subice waters where liquid conditions and chemical energy remained available. It is not proof of a specific Precambrian refuge, but it is a compelling real-world example that such refugees are plausible. The marine connection matters in this context as well. If the original water was seawater or strongly marine-derived, later trapped and altered beneath ice, then Blood Falls also shows how ancient coastal or fjord environments can be carried forward into much later continental settings. The 2019 geochemistry paper states that the original water now preserved as glacial brine is most likely ancient seawater, and that Taylor Valley may once have been a fjord or inland sea, before changing climate and glacier behaviour isolated and transformed that water. That means Blood Falls is effectively a surviving chemical thread linking three very different Earths: a more marine Taylor Valley, a colder glacially reorganised valley, and the modern dry polar desert. Very few places let you see that kind of continuity in one phenomenon. It also tells us something practical about how old environments become inaccessible. The reason Blood Falls is so useful is that the brine actually escapes. Without that outflow, the buried system below Taylor Glacier might remain mostly invisible except to geophysics and drilling. The 2017 glaciology work describes an glacial brine system that functions as an active hydrologic pathway to Blood Falls, and the 2022 astrobiology summary notes that Blood Falls lets researchers study subsurface brines and their materials in the field. That means one of the best natural records of ancient environmental persistence on Earth is available not because the record was kindly preserved in the open, but because a hidden system developed a leak. Many other ancient subsurface archives likely remain buried with no such obvious surface clue. Blood Falls is valuable partly because it reminds us how much deep time evidence is probably still concealed, and perhaps that is the broadest point of all. Blood Falls reveals that Earth's deep past is not gone in the tidy way we often imagine. It lingers in trapped waters, in altered salts, in subterranean chemical gradients, in microbial metabolisms that still make sense of ancient conditions, and in the long afterlives of climates that changed long ago. The modern red outflow is not a relic in the museum sense. It is an active process carrying old information into the present. The brine below Taylor Glacier is ancient in origin, altered over long contact with rock and repeated climatic changes, and still connected enough to the modern world to emerge and oxidize in the Antarctic air. That is why blood falls matters. It does not simply tell us that something odd is happening now. It shows that the present landscape is still being fed, literally, by pieces of Earth history that never fully ended. Once you see blood falls that way, as a working link between vanished seas, later glaciers, buried brines, and long-lived microbial chemistry, it becomes hard to keep the story contained within Taylor Valley. The obvious next question is why any of this should matter beyond one Antarctic glacier, and the answer is that blood falls reaches well past Antarctica, because it changes how we think about hidden water, hidden life, and the kinds of worlds that might still be habitable even when the surface looks finished. By the time you reach this point in the Bloodfall story, it has already done something unusual. It has moved from looking like a visual oddity to behaving like a scientific crossroads. A red outflow at one Antarctic glacier turns out to matter far beyond its own valley, because it touches several of the biggest questions modern science keeps returning to. How much hidden liquid water can survive in places that look frozen solid from above? How much of Earth's biosphere exists in dark subsurface habitats rather than in familiar sunlit ones? What kinds of chemical signatures would tell us that a seemingly dead icy world is not actually dead at all? Blood falls matters outside Antarctica, because it is one of the rare places where a hidden, iron-rich, microbially influenced brine system leaks into view and can be studied directly. The broader Dry Valleys work showed that blood falls is surface evidence of deep subsurface liquid, and that its presence helped motivate the first landscape-scale airborne electromagnetic survey of Antarctic subsurface resistivity, revealing extensive buried brine systems beneath Taylor Valley. That alone would make the site important, because modern Earth science increasingly cares about what lies beneath apparently simple surfaces. Bloodfalls tells us not to trust first impressions in cold regions. Taylor Glacier had long been treated as predominantly cold-based, the sort of glacier expected to be frozen to its bed, and not especially generous with active liquid pathways. Yet radar work later showed an active and glacial hydrologic system, carrying brine toward the terminus, while geophysical surveys showed subglacial brine-saturated sediments below the glacier itself. That matters beyond this one glacier, because it forces glaciologists to widen their models of what cold polar glaciers can hide. The Journal of Glaciology study explicitly says the existence of active water in Taylor Glacier has broad implications for cold-based glacial systems, and may require changes to glacier dynamics models in polar regions. In other words, Bloodfalls is not just about one spectacular leak. It is evidence that polar ice can be more hydraulically complex, and therefore more dynamically interesting than its frozen exterior suggests. It also matters because it enlarges the map of where life can plausibly exist. Most people still carry around a quiet assumption that a habitable environment ought to look at least a little welcoming. It should have sunlight, perhaps open water, maybe some kind of soft edge where biology can visibly take hold. Bloodfalls is useful because it takes that expectation and ruins it politely. NASA's astrobiology coverage describes the source environment as cold, dark and lacking oxygen, yet hosting unusual microbial life that appears to have adapted over roughly 1.5 million years to use sulfur and iron compounds rather than sunlight-driven production. NASA's broader astrobiology strategy then takes the next step and treats subsurface brines, saline fluids, and chemosynthetic communities as highly relevant to the search for life elsewhere in the solar system. What Bloodfalls shows is not simply that life is tough. It shows that habitability can be chemically built and physically hidden, with no requirement that the surface advertise it in ways humans find intuitive. That is where the story leaves Antarctica and starts speaking directly to Mars. The McMurdo Dry Valleys are already widely used as a Mars analogue because they are cold, arid, salt-bearing, and geologically exposed in ways that resemble some Martian surface environments. Bloodfall sharpens that analogy by adding a buried brine system beneath a landscape that, from the outside, looks dry and frozen. The 2016 Scientific Reports paper on Antarctic continental brines notes that interest in cold brines increased after brines were identified on Mars, and that such environments may represent potential subsurface habitats. NASA's astrobiology strategy likewise frames improved understanding of subsurface life, brine stability, and chemosynthetic organisms as directly informing investigations of Mars, especially in the subsurface. Bloodfalls therefore matters beyond Antarctica, because it offers a real example of how a planet or planetary body can look hostile at the surface while still sustaining liquid saline environments below, complete with redox chemistry and microbial potential. That is a much more useful lesson for Mars exploration than any amount of vague talk about extremophiles in the abstract. It matters just as much for icy moons, perhaps even more. Europa and Enceladus are compelling because both appear to host liquid water beneath thick ice, and both invite the same basic question that Bloodfalls has already helped us ask on Earth. If chemistry, liquid water, and isolation come together under ice, what can persist there? NASA's astrobiology news on subglacial lakes notes that such environments on Earth are excellent places to test technologies and techniques for future missions, specifically because moons like Europa and Enceladus harbour oceans beneath icy shells. NASA's coverage of icy world analogue sites goes further and identifies Bloodfalls as one of only 2 known Earth analogue sites involving sulfur or iron on ice, with direct relevance to the interpretation of coloured material and chemistry associated with Europa's icy surface. Bloodfalls matters because it gives planetary scientists a grounded example of how iron-rich or sulfur-rich staining on ice may represent deeper chemical stories, not just superficial decoration. That last point is especially valuable because space exploration often has to work backward from surface clues. On Europa, for example, scientists cannot simply drill through the whole ice shell tomorrow and have a look around. They have to infer from colour, chemistry, structure, and whatever material reaches the surface. NASA's Icy World Analogue article notes that Europa's surface shows reddish-brown markings, and that iron and sulfur associated with those terrains have prompted scientists to think carefully about ocean chemistry below. It then places Bloodfalls in that context as a terrestrial analogue where iron-rich material emerges onto ice and can be studied directly. Bloodfalls does not tell us that Europa's red features are biological, and responsible scientists do not pretend otherwise. What it does do is train the imagination and the methods. It reminds researchers that discoloured ice can be the surface expression of subsurface water rock chemistry, salt transport, and possibly life-relevant redox systems. That is a much more disciplined and useful lesson than simply saying, Antarctica is kind of like space, which is true only in the broadest and least helpful sense. There is another reason Bloodfalls matters for worlds beyond Earth, and it is more practical than philosophical. If you ever hope to search an icy moon for life, you have to solve an awkward engineering problem first. How do you reach buried ice or brine cleanly enough that your instruments do not contaminate the thing you are trying to study? Bloodfalls has already served as a proving ground for that sort of technology. The Ice Mold project, described in Annals of Glaciology, was developed specifically for clean in situ analysis and sampling of subsurface ice and subglacial materials, with Bloodfalls named as an intended test site. The same paper states that the technology is especially promising for future extraterrestrial applications, and that its design was adapted in part with exploration of icy moons such as Enceladus in mind. NASA's subglacial lake coverage similarly says Earth's hidden icy habitats are excellent places to test techniques for missions beyond our planet. So Bloodfalls matters because it is not just a natural analogue, it is also a field laboratory for learning how not to ruin an alien ecosystem before you have even measured it. That clean access problem may sound technical, but it is actually central to astrobiology. If a robot drills into an icy environment on another world and brings Earth microbes or organics with it, then every later detection becomes suspect. Bloodfalls offers a place to develop protocols under real conditions rather than perfect laboratory ones. The IceMole paper emphasises microbiologically clean access, environmental stewardship of fragile subglacial ecosystems, and sterilisation according to planetary protection style standards, while also highlighting the device's ability to navigate through cold ice, avoid drilling fluids, and collect subglacial material without external contamination of the sample. That makes Bloodfalls matter beyond Antarctica in a very literal sense. It helps bridge the gap between astrobiological theory and the ugly practical business of actually sampling buried ice without lying to yourself about what you've found. The site is scientifically important, not only because of what it contains, but because of how it forces researchers to behave if they want defensible answers. It also matters because it gives scientists a rare chance to compare what a hidden biosphere looks like in the subsurface with what becomes visible after exposure. The Frontiers Mineralogy study concluded that the red colour arises when dissolved. Fe2+ in the subglacial fluid oxidizes upon exposure to air, forming amorphous iron-rich nanospheres rather than the neat crystalline phases many people expected. The authors explicitly note that this mineral assemblage could indicate a habitable environment if found elsewhere in the solar system. That is a powerful statement, not because it proves life elsewhere, but because it strengthens the chain from environment to signal. One of the hardest problems in life detection is deciding which surface materials truly point back to a habitable or inhabited subsurface. Bloodfalls helps because the hidden source environment is already relatively well studied, allowing scientists to connect buried chemistry, microbial ecology, and visible mineral products in one real system rather than in separate thought experiments. There is also a more earthbound but equally important reason this site matters beyond Antarctica. Bloodfalls is part of the evidence that the deep biosphere is not some marginal curiosity tucked away beneath the more glamorous surface world. The Nature Communications paper describes Bloodfalls as evidence of deep subsurface liquid in the dry valleys and notes that the brine contains diverse microbial community that actively influences weathering and the geochemistry of the fluid by liberating ions such as iron and silica from subglacial bedrock. That means the site is important not only for the search for alien life, but for understanding how life reshapes hidden environments on our own planet. If microorganisms in buried Antarctic brines can alter mineral weathering, iron chemistry, and fluid composition, then subsurface life is not merely surviving. It is participating in planetary geochemistry. Bloodfalls therefore matters because it pushes the deep biosphere toward the centre of the conversation, where it belongs. And then there is the ecological side. Bloodfalls is easy to think about as a stain on ice, but its discharge affects nearby systems too. The 2026 Antarctic science study linked an observed Bloodfalls outflow event to glacier surface lowering and a cold temperature anomaly in the west lobe of Lake Bonny, underscoring how short-lived subglacial drainage can perturb lake conditions and potentially alter nutrient transport. That matters because it reminds us that hidden hydrology does not stay hidden in its consequences. A pressure-driven brine release under a glacier can ripple outward into nearby lakes and ecosystems, changing temperature structure, chemistry, and nutrient supply. Beyond Antarctica, this matters for any effort to understand how buried water systems under ice influence broader ecological and geochemical networks. whether on Earth or on another icy body where surface or near-surface signatures might be episodic rather than constant. Blood Falls is a lesson in coupling. The hidden system and the visible landscape are not separate stories. They are one story with delayed communication. It even matters for remote sensing, which is one of those phrases that sounds dry until you realise how much of planetary science depends on it. NASA's Icy World Analog article explains that fieldwork at analog sites helps researchers identify and characterise biosignatures, calibrate remote sensing with ground truth, and improve confidence in interpreting spacecraft data from icy moons. Blood Falls fits that program beautifully, because it lets scientists study how a real, subsurface chemical system expresses itself at the surface in colour, mineralogy, and spatial pattern. If you want to know how to interpret discoloured ice or chemically unusual surface deposits on another world, you need places on Earth where the source environment is partly known and the surface expression can be measured carefully. Blood Falls is one of those rare places. It is not just a natural wonder. It is a calibration target for the imagination, which scientists often need as much as they need better instruments. There is also the question of what sort of worlds we should stop underestimating. Before places like Blood Falls were studied in detail, a cold, dark, oxygen-poor brine under an inland glacier would have looked like a fairly poor candidate for an active ecosystem. NASA's 2009 coverage says exactly that. These were conditions under which scientists previously believed nothing could survive. The wider astrobiology strategy now treats subsurface saline environments and the adaptations of life to them as having broad implications for the search for life in the solar system. That change in perspective is part of Blood Fall's real legacy. It is not simply that the site is unusual. It is that the site helped move scientific culture away from an overly surface-based, oxygen-based, sunlight-based sense of where habitability begins and ends. Beyond Antarctica, that shift affects how missions are designed, which planetary bodies are prioritised, what measurements count as meaningful, and how sceptical or open-minded researchers ought to be about hidden liquid environments. So when people ask why this bleeding glacier matters beyond Antarctica, the answer is not just that it is a nice analogy for space, or a dramatic visual hook for documentaries, though it is both of those things. It matters because it demonstrates that a buried, ancient, chemically powered ecosystem can survive under thick ice and still leave interpretable signals at the surface. It matters because it changed how scientists think about cold-based glaciers, deep groundwater, and subsurface connectivity. It matters because it offers a real Earth example of the kind of hidden brine habitat that could exist on Mars or within the icy shells of ocean worlds. It matters because it helps build and test clean access technology for future exploration. And it matters because it reminds us that some of the most important habitats in the universe may not be the ones that look alive from the outside at all. Blood Falls turns a red stain into a set of instructions. Look beneath the surface, expect chemistry to do strange things, and do not mistake silence for emptiness. Once you know that, the place stops feeling like a freakish accident and starts feeling like something stranger and somehow calmer. A natural scene whose beauty comes not from being pretty in the ordinary sense, but from being so unlikely, so severe, and so completely itself. There is a particular kind of beauty that only appears once the first surprise is worn off. It is not the easy beauty of something obviously pretty, the kind that asks for nothing more from you than a glance and a quick agreement. It is the beauty of something that begins by seeming wrong, then slowly reveals that wrongness to be the exact point. Blood Falls belongs to that category. At first it looks like a mistake in the landscape, a red wound opened in a white glacier, a visual contradiction in one of the coldest and driest places on Earth. Then the explanation arrives. The water is not blood but iron-rich brine. The red appears when dissolved iron in the outflow oxidizes after reaching the air, forming iron-rich materials that stain the ice. The fluid itself comes from an ancient hypersaline subglacial system, connected to Taylor Glacier and the wider hidden hydrology of Taylor Valley. Once all of that is understood, the place does not become less beautiful. It becomes beautiful in a more serious way because you're no longer looking at a mystery in ignorance. You're looking at a mystery that survived explanation. That is a rare outcome. Many things are fascinating right up until the moment you learn how they work. A stage illusion is wonderful until someone shows you the mechanism, at which point it becomes less magic and more respectable carpentry. Bloodfalls moves in the opposite direction. Knowing the mechanism deepens the effect. The red stain is no longer just a dramatic colour contrast. It is the visible sign of chemical change, pressure, ancient marine history, rock-water interaction, subglacial storage, and microbial persistence in darkness. The outflow is not merely striking, it is layered. The lower Taylor Glacier and Bloodfalls are formally protected as an Antarctic specially protected area, because the site is significant for glaciology, geomicrobiology, paleoclimate interpretation, and the study of subglacial processes. That is a wonderfully sober administrative way of saying that this one red seep has become one of the most scientifically revealing places in Antarctica. And yet, even with all that science attached to it, Bloodfalls keeps its emotional force. It still looks startling. It still looks a little impossible. It still catches the eye in the way only a strong violation of expectation can. Antarctica trains us to think in pale terms. White, blue, grey, black rock. Perhaps the faint brown of exposed sediment, but mostly a restrained palette. Bloodfalls interrupts that restraint with a colour humans have never been good at ignoring. We are built to notice red. It signals food, heat, warning, urgency, ripeness, injury. On a glacier, where none of those categories make much sense, the colour becomes even more powerful because the mind cannot immediately file it away under anything ordinary. That first moment of confusion remains part of the beauty even after the chemistry is understood. The place still catches at the nerves a little before the intellect catches up. I think that matters because beauty is often described too politely, as if it were always soft or welcoming or obviously pleasant. But some things are beautiful because they refuse to fit the easy categories we use to feel in control of the world. A storm can be beautiful. A volcanic plain can be beautiful. A bare desert can be beautiful in a way that has nothing to do with comfort. Bloodfalls belongs to that harsher family of beauty. It is severe, spare, and oddly intimate all at once. Severe because the setting around it is so stripped down. A cold desert valley with little softness to absorb the scene. Spare because there is almost nothing in the visual field to compete with the red. And intimate because the outflow has the unsettling look of a bodily event, even though it is entirely geological and chemical. It feels as though the glacier has briefly revealed an inside. That sense of interiority may be the deepest source of its strange beauty. Glacier is supposed to be surface mass exterior. Bloodfalls makes it feel like a body with hidden circulation. Of course, it is not a body. And that correction is part of the fascination too. What looks biological is not biological in the familiar sense. No wound, no flesh, no blood cells, no injury, no heartbeat. Just brine, salts, iron, pressure, and time. Yet the analogy persists because it is visually irresistible, and perhaps because it gives us a language for what would otherwise be too abstract. Most people do not carry around a ready emotional response to phrases like marine-derived subglacial brine, or mixed valent iron-bearing nanospheres. But everyone understands, immediately and viscerally, that something red running down a pale surface demands attention. Bloodfalls lets the language of the body borrow the stage for a while, before science gently takes it back. The 2022 mineralogical work makes that handoff even more satisfying, by showing that the red surface materials are not simply ordinary crystalline rust, but tiny amorphous iron-rich nanospheres formed after the brine emerges and encounters oxygen. That means the beauty of the place is tied not to a fixed pigment, but to a transition, a moment when hidden chemistry becomes visible. There is another reason the site feels beautiful in a way that is hard to put down. and it has to do with proportion. Bloodfalls is not large in the way mountains are large. It is not grand because of size. Its visual power comes from scale held in tension. The outflow itself is relatively small, but the system behind it is vast by implication. A thin red stain on the glacier face points back to brine-saturated sediments beneath Taylor Glacier, to hidden pathways within the ice, to ancient seawater or marine-derived salts altered over immense stretches of time, and to a microbial world sealed in darkness for possibly hundreds of thousands to more than 1 million years, depending on which part of the system is being discussed. The visible object is modest. The invisible context is enormous. That disproportion gives bloodfalls a very particular quality. It looks like a detail and behaves like a world, and perhaps that is why so many people remember it once they have heard about it. Not because it is pretty in the usual travel poster sense, but because it feels like one of those places where Earth briefly drops its plight surface and lets you glimpse the machinery underneath. Most landscapes do not announce their hidden chemistry so clearly. Groundwater moves underground and remains underground. Mineral reactions happen in darkness. Microbial communities persist where nobody sees them. Ancient environmental histories remain written in sediments and fluids that never rise to meet the eye. Bloodfalls breaks that habit. It is a leak in more ways than one. A leak of brine, yes, but also a leak of information. A signal from an unseen system. That kind of accidental revelation has its own beauty, because it makes the planet feel less finished and more alive in the broadest possible sense. The setting contributes to all of this more than it first appears to. Taylor Valley is already one of the strangest landscapes on Earth. A cold desert in Antarctica, where bare ground, frozen lakes, katabatic winds, and limited seasonal melt create an environment that seems to have had all excess life and softness edited out of it. The McMurdo Dry Valleys are often treated as a Mars analogue because they are so arid, cold, and exposed. In that landscape, bloodfalls feels doubly improbable. A red outflow would be surprising anywhere, but here it arrives in a place where even ordinary liquid water already feels special. The valley does not distract from the phenomenon. It prepares it. The silence, the barren rock, the permanent ice cover on nearby lakes, the sense of distance from everything familiar. All of that sharpens the impression that this is not supposed to be happening here. And that is exactly what makes it visually unforgettable. Beauty also has something to do with restraint, and Bloodfalls is oddly restrained despite the name. It is not erupting violently. It is not some roaring torrent in crimson foam. It seeps, stains, spreads, and darkens the ice with a kind of quiet insistence that matters. The phenomenon would be less haunting if it were bigger and louder. Instead, it behaves in a way that matches the valley, measured, sparse, not eager to explain itself. Even the new work on discharge timing and glacier motion reinforces this sense of controlled release. The 2026 Antarctic science paper linked Bloodfall's outflow to subtle glacier surface lowering and interpreted the event as subglacial brine being forced out as the glacier's weight and hydrologic system changed. That is a dramatic result scientifically, but physically it remains a matter of millimeters, pressure changes, and a stain emerging from the glacier face. The beauty of Bloodfalls is not spectacular in the usual sense. It is concentrated. I suspect people respond to that because it feels more honest than grandeur. The world is full of large things that are impressive simply because they are large. But Bloodfalls has to earn its effect through structure and meaning. It asks you to look closely. It asks you to tolerate not knowing, then to accept a more complicated answer than the first impression offered. It asks you to hold together the emotional force of the image and the technical specificity of the explanation without sacrificing either. That is not the most common kind of beauty, but it may be one of the most durable. Once you know what Bloodfalls is, you do not just remember a picture. You remember a chain of ideas: ancient marine water, cryoconcentration, subglacial, brine, ion oxidation, sulfur cycling microbes, hidden hydrology, a glacier acting as a pressure release valve, a red stain produced at the boundary between darkness and air. The beauty becomes intellectual as well as visual, and the two parts strengthen each other rather than compete. There is also something moving about the fact that Blood Falls is beautiful precisely because it should not exist according to our simpler expectations. That phrase, should not exist, does not mean it violates physics. On the contrary, it is deeply physical. It is a product of chemistry, glaciology, hydrology, and microbiology doing exactly what those sciences say they can do under the right conditions. What it violates is the lazy version of reality, the simplified mental sketch most of us carry around when we're not looking closely. Glaciers are frozen, Antarctica is white, dry valleys are dry, sunless buried water should be inert, harsh places are empty. Blood Falls contradict every one of those simplifications without breaking a single real law of nature. And there is beauty in that too, in being reminded that reality is more inventive than the shorthand we use to navigate it. That lesson reaches beyond aesthetics, of course. Blood Falls has become important to astrobiology because it shows that life can persist in cold, dark, hypersaline environments beneath ice, using chemical energy rather than sunlight. It matters for understanding hidden habitats on Mars, Europa, and other icy worlds. It matters for how we interpret coloured materials on ice, how we think about subsurface brines, and how we design clean technologies to access buried environments without contaminating them. But even that scientific importance folds back into the beauty of the place, because it makes the outflow feel not just local, but cosmically suggestive. A red seep in Antarctica becomes a clue about where else in the universe hidden chemistry and hidden life might be waiting. The site is beautiful, partly because it is specific, but also because it opens outward so naturally into larger questions. If all of this sounds a little serious for a waterfall, that may simply be because Blood Falls is not really a waterfall in the ordinary sense either. It is not a mountain cascade or a river drop. It is a seep from an ancient subglacial system, coloured after emergence, episodic in release, and chemically out of step with the world above it. The word waterfall belongs mostly to our need for familiar categories. We hear falling water and apply the label. Nature, as usual, is under no obligation to make the label especially neat. What exists at Taylor Glacier is stranger than a normal waterfall and, for that reason, more memorable. It gives us the shape of something familiar while filling that shape with processes most people would never have guessed. And perhaps that is the most satisfying way to leave it. Not as a freak show of Antarctic geology, not as a scientific curiosity exhausted by explanation, and not even as a cautionary tale against making assumptions, though it is all of those in part. Better to leave it as an example of how the planet can still surprise us without abandoning rigour. A place can be fully explained and still feel uncanny. A landscape can be chemically understood and remain visually arresting. A hidden system can be mapped, sampled and modelled without losing the sense that it is, in some deep way, more inventive than we expected. Blood Falls is beautiful because it sits exactly at that intersection. It is what happens when severe geology, ancient climate history, buried water, microbial persistence, and a very human response to colour all meet in one small place on the edge of a glacier. So if you picture it now, picture it clearly. Not as blood, not as a wound, not as some melodramatic accident in the ice. Picture Taylor Glacier in the dry valleys, the cold desert around it, Lake Bonny nearby under its perennial ice cover, and within the glacier and beneath it, a hidden brine system connected to a much older history than the modern landscape reveals. Picture that clear, iron-rich, oxygen-poor fluid reaching the surface at last, then reddening in the Antarctic air as the chemistry changes. Picture the stains spreading downward across pale ice, small in size and enormous in implication. A quiet outflow, a chemical confession, a reminder that even in one of the most seemingly lifeless places on Earth, there are processes still moving, still reacting, still carrying the deep past into the present. And that really is why the place stays with people. Not because it is monstrous, and not because it is pretty in the obvious sense, but because it brings together two feelings that do not often coexist. It is unsettling and clarifying at the same time. It looks like something impossible and turns out to be something entirely real. The explanation does not flatten it. It reveals its depth. A waterfall that should not exist does exist, but only because our first idea of what is possible under ice was too simple. Bloodfalls corrects that idea gently but permanently. After it, Antarctica feels less empty, glaciers feel less closed, and beauty feels a little broader than before. Sleepy, perhaps, is not the first word anyone would reach for while standing in front of a red seep on a frozen continent, but there is a calm in it once you know what you're looking at. A calm in the patience of the chemistry, in the age of the water, in the quiet persistence of life below the ice, and in the thought that the Earth is still capable of holding hidden worlds until the moment one thin red line appears and tells us to look again.